All right, guys, here we go. So Big Idea 2, we're going to look mostly at IMFs and properties of matter. Just as a review, ionic compounds are going to, metals and nonmetals are big differences in electronegativity. High melting point, solid. This is a big one that they will use in the AP exam. They don't conduct electricity as solids, but when they're dissolved, they will. So most of them are soluble in water, but some are not as soluble. For example, your halogens bonded to mercury, lead, and silver. You can remember small, medium, and large. That's how I remember, like S and L, small, medium, large, were your halogens. Covalent, they have to overcome IMFs. Now, something like water is going to have stronger IMFs than something like iodine. Like this is a polar compound with hydrogen bonds. Iodine is just a molecular solid. We're going to get into that. They don't conduct electricity ever. Your network covalent, that's going to be really strong covalent bonds there. So you're going to have high melting and boiling points because instead of overcoming IMFs, you're actually going to have to break covalent bonds here. Solid, they don't conduct electricity except for graphite because they have delocalized electrons. Graphite only forms 3 bonds instead of 4, like most carbon. So you have some electrons that are delocalized, like pi electrons. Anyway, metallics, bonds, they have high boiling melting points, they're solid, and they will obviously conduct electricity. There's a little virtual lab here, if you need to look at that later. So least soluble at room temperature, this is a quick question, so you can take a look at that. So I see you guys have already picked your answers. If we look, A is potassium nitrate, so that's ionic. This is methanol, and that's ethanol. Now, this hydroxyl group here on these alcohols will be able to hydrogen bond with water. Ethanol is going to be less soluble than methanol, though, because you have this part of the molecule is going to be nonpolar, and so that nonpolar part of the molecule won't be able to overcome the hydrogen bonds in water to become soluble. And this last one, which I guess is just hexane, totally nonpolar, so least soluble. Okay, acid strength. This is pretty tough. Oxyacids, so we're going to look at just this side, okay? Oxyacids, they are going to be based on electronegativity. So when you're looking at this, you kind of have to think about it like almost like a tug of war. And in my classroom, I kind of show this with some Play-Doh. So if I have, this is my proton, and if I think about water here, my little negative dipole on the oxygen, I can think about those. I'm just going to draw them in for you. And this is going to be the positive dipole of the acid. So you have the dipole-dipole interaction here. Now, what's going to have to happen for this acid to get deprotonated is the dipole-dipole interaction has to be stronger than this covalent bond right here. So what occurs is with an oxyacid, as I start to add oxygens, right here I have 2 and then I have 3, those oxygens are really electronegative, which is how strongly an atom can pull electrons toward it in a bond. So if I think about this bond here, and if you think about like a ball of Play-Doh, what ends up happening, I have a ball of Play-Doh, and as I add oxygens, that's going to become kind of thinner. Like if I could just pull a piece of Play-Doh and make it thinner and thinner and thinner. Because this side of the molecule, in these situations here, they're going to be able to pull the electrons away from this bond. And as it does, it's going to weaken that bond, weaken it to the point that this hydrogen here is going to be able to join in with the water and make a hydronium. That H3O plus that you always see when you're talking about acids, that is this, and this is how it happens. So, in this situation, with the perchloric acid, anyway, this hydrogen here is going to be able to be deprotonated, or this acid will be deprotonated by this water because all the more easily than HClO3, because you have more oxygens pulling the electron density away from that bond. That's kind of complicated. When you're dealing with oxyacids, you're just going to be looking at that electronegativity of what is bonded to the hydrogen. So, on another note, differently, separately, when we have binary acids, in this situation, we're going to be thinking more about coulombic attraction and distance. So, hydrofluoric acid is the weakest acid if we look at, HF, HCl, HBr, and HI. In this situation, your hydrogen, right, hydrogen and then your iodine, hydrogen, and your bromine. I mean, this is not to scale, so you're going to have the least amount of, these should be touching or closer, but you're going to have the least amount of coulombic attraction between the H and the I. So this is going to be more easily deprotonated than, HCl. So this is your strongest acid. Now, if I look at hydrogen bonded with things in groups 16 or 6A, these are going to be, when we look at the charges of oxygen, all these groups 6 or 16, things are 2-. So these are actually going to be weaker than their counterparts because of the increase in charge there. So the question for this one is a little bit tricky. If I pull it up, you have to ignore the writing. I have to pick one or the other. So the weakest acid here, I'm going to be looking for the one that only has 2 oxygens first of all. And then I have to ask myself about electronegativity of what it's bonded to. So you guys take a second to think about that. All right, you got it? Right. So if I'm looking for the weakest acid, bromine is going to be less electronegative than chlorine, and then it has only the 2 oxygens, pulling the area of electron density away from that hydrogen atom, and so it can be deprotonated easier. This is the easiest slide in the PowerPoint, so let's just take a moment of silence to appreciate this. Solids are in a pretty fixed position. They're still vibrating and wiggling around a little bit, but they're not completely stationary. That only happens at absolute zero. Sorry, beyond the scope of the course. Liquids are moving around randomly, and the gases are pretty far apart. Kinetic molecular theory. They'll use this in ways to trick you. So let me tell you how you may be tricked. First of all, there are lots of tiny particles. They're pretty far apart if you think about their size in relation to volume. There are elastic collisions, so you're not losing any energy. They have continuous random motion, and there should be, ideally, no interaction between molecules. That's not really true, right? Because some molecules are polar, and then once you start to reduce that volume and lower the temperature, things start to go a little crazy. So here we go. This first one is kind of a big deal. If the temperature is not changed, no matter what else is listed in the problem, the average kinetic energy of a gas doesn't change, okay? So what they'll do is they'll say 2 gases are at, 100 degrees Kelvin, and then they put them in a different chamber, or they put it somewhere else. It doesn't matter. If that temperature doesn't change, the average kinetic energy doesn't change, because that is the definition of temperature. All gases begin to act non-ideally when they're at low temperatures or high pressures because of the particle interactions. So the easiest way to think about when gases start to act non-ideally, think about what would cause a gas to condense. So you're going to have low temperatures that would cause them to condense. And if you had really high pressures, or 2, if you think about having stronger intermolecular forces, like for example if it's polar, that would cause it to be more likely to condense. So those are the things that are going to cause a gas not to act ideally. So under the same conditions, the stronger the intermolecular attractions, the less ideal. Okay, so I just kind of talked about that a little bit. So which combination of conditions, remember what I just told you, pressure, temperature, and number of moles respectively, are most ideal?
So remember, your pacing is about 1.5 minutes on these, and some of the multiple choice involves a lot of math, so you may need more time. All right, looks like you got it. So it's going to be D, because the pressure being low is going to reduce the number of collisions and chances for condensation. High temperature keeps them in motion, and then the low number of moles. So remember, those low temperatures, those are going to cause a gas to become less ideal because they're going to start to condense, and you're going to have more of those collisions not really being elastic. They're going to start to make liquids. All right, so properties of gas and factors. You shouldn't worry about individual gas law names. So listen, if it's talking about pressure and volume, for example, and you need to describe that, you don't say Boyle's. That's not going to get you any points. So any names of any scientists, that's great. Like, I'm proud of you, but you don't mention the names. It won't get you any points. Okay. So Boyle's law, pressure and volume, at a constant temperature and amount of gas, pressure decreases as volume increases. So if you recall, the pressure and the volume here are, right, they're multiplied together. Volume and temperature, so Charles' law, that's going to be this guy, and then volume and moles. If you think about it, these have to, equal a constant. And so when I'm doing math, if I increase pressure and I still have to make these two things multiplied equal a constant, if I increase pressure, my volume has to decrease, or if I decrease volume, the pressure is going to increase, right? And so here we see that we decreased the volume, so the pressure's got to increase. Or I think I said that wrong. I increase the volume, so the pressure is going to decrease. Excuse me. When things are divided, so that is that inverse relationship. Okay? When things are divided like this, if I still have to equal a constant, if I increase that volume, then the temperature is going to have to come up too, because when I divide them, I'm still going to have to get the same number. So things that are divided when you rearrange formulas, or you have the formula, they're directly related. So as volume goes up, so does temperature. Let me see that here. Same thing with volume and moles. As the volume goes up, then the number of moles will increase, or vice versa. All right, so that's a little math review for you. So use the kinetic molecular theory of gases to predict what would happen to a closed sample of a gas whose temperature increased while its volume decreased. So you can reason your way through this. You know how those formulas, so you can write them down, whichever one helps you. I like to look at the formula and think about it mathematically. That's how I think, but I hope when you read letter A, you said no because the temperature was held constant. Like, even if you don't get it right, I hope you don't pick that one. You guys got it?
Are you saying no because the temperature is so constant?
Yeah, if you, oops. So you still shouldn't have picked A. Y'all gotta keep me straight. The temperature, they do that a lot though, so I'm so leery of questions that have this. But you still should have picked A because the temperature increased, and so definitely the average kinetic energy would increase. Which, that's what I meant to say. So, still not A. Did you pick another answer? All right, good. I'm glad y'all got it figured out because y'all have to take the exam. So the pressure would increase. So if we think about it, what I had told y'all, pressure and, here it is right here, pressure is multiplied by volume. And so if they're equal to a constant, if I decrease the volume, then the pressure is going to have to come up to still equal that constant when I multiply them. So that's D. All right, yay, math. Because you don't have a calculator on the AP exam, right? They're not going to expect you to do really esoteric calculations. So this one's good. It makes you set things up, but you don't have to. You don't have to actually work it out. Now, do recall with gases, you're always going to have to convert to Kelvin. But go ahead and give this one a try. 15.5 grams of an unknown substance. Placed in a sealed 5-liter container, 150 degrees Celsius. The pressure in the container is 1.1 atm. So go ahead and get that worked out. Warm up your brain. Remember how the ideal gas law works. You guys got it? Yep. Pretty straightforward. You're just filling this into good old Pivnert and, rearranging it, right? No problems. So when you do that, the correct answer is E. And so the thing is, with molar mass, if they ask you for molar mass and you don't really have enough information, you kind of start to freak out a little bit, don't freak out. Just always go back to the fact that molar mass is equal to grams per mole. Right? If I ask you the molar mass of sodium right now, like off the top of your head, you would be your periodic table and you would tell me it's, 22.99 grams per mole. Like grams per mole means grams divided by moles. And so if you're ever asked for the molar mass, you can write molar mass equals to grams per mole and fill it in. So in this situation, you got it now? Oh.
Yeah, I did it in my head.
Oh, okay. Well, yeah, don't do it in your head. So to calculate the molar mass, you're going to need to take those grams of the unknown and divide it by how many moles. And so when you rearrange it, that's what you end up getting there. So when I was teaching you in the fall, like that happened a lot when you're asked for a molar mass, and it could be on like one of the Filtrate lab questions or something like that. You just get to the end and you're like, I don't know, but you can find grams and you know the moles and you just divide them, so don't let that worry you. All right, chromatography. The picture for this one is a little bit simplified. Let me make this as easy as possible for you, okay? If you have your solvent down here, right, it's going to travel up whatever medium you're using. And the picture is not the best, so let me just add in some notes of my own to kind of help you out. Let's just say that maybe my solvent here, let's just go with water, okay? Okay. And let's just say, that's polar, right? And let's just say that the medium that we're using to do the chromatography, let's just say that this is something that's less polar or non-polar, okay? If we dissolve something in this water, or if we're trying to find some information about these little dots in this paper, whether it be ink or, it could be chlorophyll, whatever. What's going to happen is, let me change a little bit. I was trying to make it more simple. I have to change my pictures now. What has the most in common as far as IMFs and polarity with your solvent, which in this case is water? It's going to travel and stay with the water, okay? But whatever's non-polar, which in this case, like if I had some thin film that wasn't very polar, okay, it would actually move the least. It would want to stick more to the paper because it has similar polarity. Right? And you won't say light dissolves light, but the intermolecular forces between those two would cause them to stay together. That makes sense? Do you want me to maybe flip it around? Like use the picture? Yeah, okay. This is kind of confusing, so.
No, I thought it was.
Okay, so in this case, let's say we have something, let's get rid of the water. Like I said, I'm trying to simplify. I think the picture doesn't completely do this justice. Let's just say that we have a non-polar solvent here. And we have some little drops of whatever, okay? And let's say that we have polar paper. Now paper is polar, right? It has, the cellulose has little hydroxyl groups in it, hydrogen bond, and that's how, plants work with capillary action and all that. Anyway, so I have some paper, and paper's polar, okay? And then my solvent here is nonpolar. Whatever is nonpolar will be carried by the solvent the farthest. Alright, so if this is nonpolar, right, this one, according to the picture, if I go with the picture, it would be carried the farthest, okay? Wouldn't be attracted to the paper, right? It's not going to be able to hydrogen bond with the paper. It doesn't have a dipole-dipole interaction with the paper. This dot, whatever it was, this substance, it's going to just stay dissolved in the solvent because it's not going to have those dipole-dipole interactions or hydrogen bonds or whatever, okay? Now this one here, this one here, it would be the most polar because it would be attracted to the paper. It wouldn't be carried as far by the non-polar solvent, okay? So, think about it like this. Whatever this substrate is, if something stays here at the bottom and doesn't move very far, it has similar intermolecular forces with the substrate. If it's moved by the solvent, they go a long way together, then they're probably getting along. I mean, don't simplify it too much. But it has similar intermolecular forces with the solvent. Okay. So it's going to stick to whatever it's most similar to. If it sticks with the solvent and gets carried far, has similar intermolecular forces. If it doesn't go very far, then it has more in common with the substrate, whatever it is, whatever you're using. Could be thin film or paper, or there's column chromatography, there's all kinds, but that, if you can understand that, then you'll be able to answer the questions that they'll pose to you, okay? Did that clear up a little bit? Okay, good, all right, great. So here's the thing, and they've actually asked this before, like for you to draw these particulates, and you're like, oh, I got this circle thing, that's not a problem. But talking to people that grade this, it apparently is a problem. So you're starting with this lattice, or this crystal of sodium chloride. Please remember that the negative dipole of the water is the oxygen, and so it's going to surround, there's your little negative dipole sign, it's going to surround the positive ion. And notice that the sodium is going to be smaller than the chloride. Okay, the chloride is going to be a little bit bigger for two reasons. The sodium is when it becomes a cation, it's then only going to have two energy levels, right? Its electron configuration of sodium as an ion ends in 2p6. Right? Chlorides is going to actually end in 3p6, so it has a whole nother energy level, and then also when it gains that extra electron, it's going to have increased repulsion of the inside the electron count. It's going to actually make the electron count larger. And I know this is simple, I don't care. When you lose an electron, it's like losing weight, you get a little bit smaller. When you gain an electron, it's like gaining weight, and you're going to get a little bit bigger. I explained the science to you just then, but if you're taking a test and you're freaking out, you can think about that. It might help you get some things going in your head. So pay attention to size. Draw the charges on the ion, but not on the water, right? When you notice that these are indicating dipoles, this is not a hydrogen ion. It's in a bond. There's no charge on it. That side of the molecule here is positively charged, and so we're going to indicate that with a little positive or negative dipole. But don't draw charges. Don't go oxygen 2-. Don't do that. Draw at least 3 molecules of water around each, and the negative dipole points for the cation, and the positive will point to the anion. So that's pretty simple. But if you were given this picture, and this picture didn't have Na and Cl in there, but it was different colors, and it said this is a crystal sodium chloride, you would have to know and think about, hey, that sodium is going to be smaller than that chlorine. So do pay attention to that. All right, so in the box below, which means on your paper, complete a particle representation of the diagram that includes 4 water molecules with correct orientation around this calcium ion. And you can tell by the font here that this is a release exam question. So this is a real AP exam question. So go ahead and get to drawing. You guys got it? I see little diagrams everywhere. Ask yourself, did you put charges on what needed a charge, which they already gave you? Did you put some on things that did need one? So far, so good. I do like that they gave you and underlined how many. Listen, the people that are grading your exam, they are going to grade it word for word based on the question. So, if you only draw 3, you may get no points. So do pay attention to that. So when you draw it in, here's the correct diagram. 1 point was earned for the diagram, and they don't have the little dipole on there or anything, which is fine. But if you did do it, make sure it's outside the molecule and it would be correct. So as far as like the negative dipoles on the oxygen. All right, if you have your Mickey Mouse ears pointing to the calcium, no points for you. Be careful. I know that's silly, but whatever. Okay, so yay, particles. Okay, so in these beakers up here, I have 50 milliliters, and these are 25 milliliters. And so the question here is rank the 6 solutions above in order of increasing molarity. And so if you remember, molarity is moles divided by liters. Pay attention to volume, and some have equal, and some may have equal concentration. Okay, so I wish you luck. Bless you. While y'all are finishing, I am just going to do some counting up on the board. See a lot of different solutions going on. That's fine. There's a lot of different ways to do this. I'll show you what I think is, simple for me. You can decide if you like it or not. Does everybody come to their couple people still working? Okay, that's fine. I think a good solid review of 4th grade math is always handy. I got you on that. So look, molarity is moles divided by liters, and this question is not asking me to solve for the molarity of these. It's asking me to rank it. And so I could sit here and convert 50 milliliters to 0.050 liters. That's not going to help me though. So what I'm going to do is I'm just going to make some ratios and then compare them. Okay. So this is 8 particles out of 50 milliliters. Okay. This is 12 particles out of 50 milliliters. This is 4 particles out of 50 milliliters. This is 4 particles out of 50 milliliters, and this is where you need to be careful. This is 2 out of 25. Now, when you're comparing fractions, you have to make sure the denominator is the same, right? Hey, 4th grade, what's up? So 4 out of 50, and then this one here is 4 out of 25. That's kind of hard to see. 4 out of 25, which is equal to 8 out of 50. So if I'm ranking them in order of increasing molarity, the one with the lowest molarity is actually going to be a tie between C, so this is C, E, and D. Did you guys find that to be true? Okay, and then, so those are taken care of. Then the next one is going to be A and F, and then the highest molarity is going to be B. So, any trouble with that one? Okay, cool. All right, cool. And so it's important for you to be able to look at a particulate diagram and say concentration really means that there are more particles in the same amount of volume, and that's a good illustration of that. If you look at the particulate views as looking through a microscope, the volume would be irrelevant. So, like what this, we kind of consulted as we made this, and what this person had told me, and I thought was a good idea, he said that if you were looking through a microscope and this was a fixed volume in a microscope, then you would get different answers. So that's just something to think about. This is my favorite slide on the PowerPoint because I made it animated. It took me like half of a year. On my deathbed, I'm going to wish for these 57 minutes back. But this is how distillation works, okay? So distill, like if you have a whiskey still, we're in Georgia, don't have or I guess it would be moonshine. Don't do that, that's illegal. But what they do when you have a still is you're actually going to boil an alcohol and water solution, and alcohol it hydrogen bonds, but overall it has weaker intermolecular forces, so it's going to have a lower boiling point. So what you do is if you have a mixture of water and ethanol, the ethanol is the caterpillar and the water is the Mickey Mouse. I hope you found that to be funny. The caterpillars are going to leave the solution first because they have lower intermolecular forces. So we're going to heat it. We're going to heat the solution. That's the first step. And so, oh, there they are. And you can see, let's go ahead and close that back door. We're having like a little cross current here. What's going to happen is they're going to vaporize. The ethanol molecules are going to vaporize and they're going to cool. And they're going to be able to be separated from the water. Now notice the temperature here. If we keep it at 78 degrees, which is the boiling point of ethanol, then only ethanol is going to vaporize. You have some vapor pressure from the water just at that temperature, and that has to be considered. But water boils at 100 degrees Celsius, so we're going to be getting out the ethanol at that point. So now if I heat up what is in this flask until it's 100 degrees, I will start to then later be able to collect the water. So I think questions in the AP exam would be related not just to how you distill something, but also to the intermolecular forces and why this occurs and why we can do that. Yes, ma'am.
Why are you doing the water heat?
You'd only have water left. I see what you're saying. Sometimes these, like when you distill oil, for example, that's hundreds of different kinds of hydrocarbons, so you would have more than 2 things in the solution. I guess you wouldn't have to do the water, and why you would do that, I don't know, to be honest with you. But if you did raise the temperature up to 100 degrees, this would be what would happen. I guess it would all be about what you were trying to go for. It's a good question. All right, so which of the following would have the highest boiling point? So this is a good old London dispersion force question. Everybody loves them. This is a quick question. I am going to take a minute to take this opportunity to draw, some atoms for you. I need a dot. I guess I have to commit to the dots. Oh, I can't draw like a little tiny freckle. I'm trying to draw 10. I give up on counting. Xenon has a lot. I'm just going to draw more. How about that? Not to scale. With my normal pen, I can make 1,000 freckles. There. How about more? More electrons. Okay, good. So the highest boiling point, I know y'all answered this pretty quickly. Ooh, they flipped them around. Let's go. There's xenon. There's krypton. Be careful. You have to be careful with stuff. So I'm like checking the periodic table. I'm checking my pictures. So the deal here, I know y'all all picked xenon, right? I see your little papers. Doing good. The trick is you can't say anything about mass. That's not a good answer. Okay. So yeah, xenon has a higher molar mass. Nope. That's true, but not helpful. So the deal is, what ends up happening with helium has 2 electrons, and so it's less polarizable. Y'all keep hearing polarizable, but let me remind you what that means. So if these are just a random arrangement of electrons, that random motion can cause them to be polarized, which means that if both the electrons or a larger number of the electrons are toward one side of the molecule, you'll have a temporary dipole. So I'll have a temporary little dipole here, a negative dipole, and I will have a temporary positive dipole. And so when we talk about London dispersion forces and temporary dipoles, that's what we're talking about. So the more electrons I have, like if this has the most, I can keep drawing, I'll be here all day. If those all kind of shift just randomly to this side, if I have a shift of electrons over here, that's what it means when I say they're more polarizable. I have more electrons, and they can, if they do create a temporary dipole, it's going to be a stronger one, okay? Which that happens. And so this xenon here that has the most electrons, it's the most polarizable, so the London dispersion forces that occur are stronger. So that is going to make it have the highest boiling point. So you've seen, most polarizable or more polarizable, but what you want to say is, xenon has the most electrons or the largest electron cloud, so it's the most polarizable. This question, isn't a free response, but you'll have to do this, obviously. So the atom with the greatest number of electrons will be the most polarizable. So pay attention to that. The answer is vital. Remember, it is increased number of electrons, not mass. It's really common for people to say, oh, xenon has the highest molar mass, so has the most London. No. Nope. So you can see in the noble gases, the boiling point does increase down that group because radon is the most polarizable because it has the greatest number of electrons. Got it? Fantastic. All right, so at which values of temperature and pressure will the gas nitrogen behave most like an ideal gas? So this kind of goes back to what we were talking about earlier with the ideal gas law in KMT. So give that one a try. Think about how to keep it a gas, how to keep it from condensing. All right, you guys got it? Okay, so again, I'm trying to keep this gas a gas. And so if think about, if you go and you can pressurize gases and make them a liquid, right? So high pressure is going to cause things to condense, and then low temperatures are going to cause them to condense. So I'm looking for the highest temperature and the lowest pressure. So that's, pretty clear answer there. Oh, I meant highest. Sorry. Least like an ideal gas. Ooh, I love that y'all are so good at this. I missed this part of the question. That's kind of important. If I had a paper, I would underline that. So, least like an ideal gas. So I'm looking for things that would make it condense. So the answer is A. That's the lowest temperature and the highest pressure. Thank you, guys. I think y'all are gonna get 5s. I don't know about me. Yay! I gotta be careful. I love hydrogen bonding. I don't know if I love it, but the AP exam sure does. So hydrogen bonding is we're looking for sandwiches. We gotta find a sandwich. Okay, and let me show you what I mean by that. Well, if you make a bologna sandwich, bologna is going to be in the middle of your sandwich. If you're making a hydrogen bond, hydrogen is going to be in the middle of your sandwich. So what you need to look for is a hydrogen wedged in between 2 pieces of bread. And this ain't like your house where you have to have the same kind of bread. You can have 1 of 3 different kinds of breads. The bread just has to be a little fun here. So it can be fluorine, oxygen, or nitrogen. So on this side of the sandwich, I need an F, O, or N, and a intramolecular bond, which is a covalent bond with hydrogen. And then I need an intermolecular attraction with the other piece of bread, which can be an F, an O, or an N. In this situation, they're both oxygens, but it would be totally cool if this was an N, and this was an F, or this was a O, and that was an F. It doesn't matter. But you're looking for a sandwich, 2 pieces of bread, F, O, or N, and there's a hydrogen in the middle. So hydrogen bonds just want to have fun. Woo! They occur in water, DNA, ammonia. Okay. I actually want to draw ammonia for you. So ammonia, if you recall, there's my nitrogen and there's my hydrogens. And then I have a lone pair on the nitrogen. Ooh. My pen doesn't make circles very well. There we go. And so this oxygen here, or nitrogen or fluorine, has to have a lone pair. And so here's my lone pair, and it can actually, if I have another ammonia, right, like I can form a hydrogen bond right here. There's my other nitrogen. Yes, an intramolecular bond here, and then an intermolecular attraction here. And so hydrogen bond is just an exceptionally strong dipole-dipole interaction. This is because of polarity, right? So this is the negative dipole of water, and that's the positive dipole of this molecule. But it has to be in these special situations to be considered a hydrogen bond. Again, this one has to have a lone pair, and so here's an example from DNA. Notice here that, check out this nitrogen, it has 1, 2, 3 bonds. How many lone pairs is it going to have, everybody? So that's 3 bonds, makes it 6 electrons. So how many lone pairs does this nitrogen have? Just 1. You can answer, it's okay. Everybody was just like 1, but silently. Yeah, so this has a lone pair, right? And so that lone pair, and then that's going to be my intermolecular attraction. That's my hydrogen bond. And then I have an intramolecular bond with another nitrogen. And notice on this part of the DNA, then I actually am going to have a nitrogen on this side and oxygen on that side, and that's fine. So there's your hydrogen bond. So your whole genetic code is held together by electrostatic attractions, and which is why you can unzip your DNA without catching yourself on fire. Because if you had to break a covalent bond every time your DNA was transcribed, I mean, the amount of energy that would be needed would be more than that would allow you to stay alive at that temperature. I mean, you could use, enzymes and stuff, but that's why. I found that to be amazing. Okay, I'm a nerd. Out. Let's zoom in on that a little bit. So here is a picture of some water molecules and some arrows. Which of the following statements are true? So go ahead and give that one a try. Are you looking for sandwiches? Are you getting hungry for lunch? Just me? Okay. You guys got it? Okay, so let's look at this. Am I having a sandwich? No, not at all. This is a covalent bond, not a hydrogen bond. This is an intramolecular covalent bond. Hydrogen bonds are intermolecular forces. Like I said, just really strong dipole-dipole interactions. So I'm looking, I need a sandwich, bread, intramolecular, check. And, you know, like I said, this oxygen has a lone pair, so I'm good. So that's one, okay? This one, looking for sandwiches, bond, intermolecular force, the bread's right. If this was a chlorine or something right here, that would not be okay, as in the F, O, or N. So that's two, agreed? Okay, this one right here, this looks like it's, yep, bond, intermolecular attraction. That one's number 3. Nope. So I count 3. And so it says 3 of the arrows point to intermolecular bonds. 3 of the arrows point to interactions that are significantly stronger than the other 2 interactions. Now, what's stronger, a hydrogen bond or a covalent bond? Yeah, so probably not that answer. 2 of the arrows point to nonpolar covalent bonds. Hydrogen, oxygen, is that polar? All day long. So we made that a lot harder than it had to be, but like I feel like we had some good discussion here because you don't really know what they're going to ask you. All right, Coulomb's law. I love Coulomb. I thank him for his work. Ionic compounds can dissolve in polar liquids like water because the ions are attracted to the positive or negative part of the molecule. Just a minute ago, when you drew the calcium and you drew the water, what has to happen, right? What has to happen for that to dissolve is the dipole of the water and its interaction with the ion has to overcome the attraction that is holding that solid together, right? So anyway, there's a sort of tug of war. The water pulls on the individual ions away from the solids, and the solids pull in those back out of the water. And so there's going to be an equilibrium, right? And so when we get to things like KSP later, yay, that will apply. So we can predict the degree of solubility based on Coulomb's law. If it's a small ion, the closer together they're going to be. So when I say the closer together they're going to be, what I'm saying is, you know, if I start out with a solid, we would want to have different colors, but we'll just go with it. If these are smaller, right, and this is a positive ion, and this is a negative ion, and that's a positive ion, right? The Coulombic attraction here is going to be stronger than in this top ionic compound. That's a negative sign, just go with it. Because Coulomb's law, remember, its charge is divided by distance. So the closer they are, the harder it is for the water molecules to pull them away from each other. The greater the charge, the harder it is for the water to pull them away from each other. And if you're ever given charge and distance, charge will trump. So like if we're talking about something that has like aluminum that has a 3+ charge, if you think about it, a lot of aluminum compounds, they're not soluble because aluminum has a 3+ charge. So predict the following pairs if they should be more soluble in water based on Coulombic attraction. So which one's going to be the most soluble? Think about the charge and the size. All right, so this is 3 separate questions. You guys got it? Oh, nope, still see some people working. So don't be like Ms. Freeman. Look and make sure you read the question right. More soluble. So we're looking for, we're going to circle or box in the one that's the most soluble in each little pair. All right, cool. So we have lithium fluoride and sodium fluoride. Well, lithium is smaller than sodium, right? So the Coulombic attraction between lithium and fluoride is going to be greater than sodium fluoride. So the one that's going to be the most soluble is going to be sodium fluoride for that reason. NaF and Kf, sodium is smaller than potassium. So for the same reason, the Kf is more soluble. And then with beryllium oxide, beryllium has a 2+ charge and oxygen has a 2- charge, so they're going to have an increased Coulombic attraction compared to lithium fluoride, which is a +1 and a -1. Even though the lithium and fluoride, we have to start thinking about the size, maybe that doesn't all work out. Well, yeah, beryllium is going to be smaller than lithium, and then oxygen is a little bit, well, that's pretty similar, but if you're even in different groups, you know, you would look at the charge more. All right, entropy in solutions. So we're going to get into entropy a little bit more with other learning objectives and different big ideas. But here's the thing. Water dissolves salts by forming a shell, and we already drew that. We already did this. We already talked about this today. So we've already made that discussion. So that weakens the electrostatic interactions between the ions, and their tendency to form like a lattice, like this little lattice. Okay. The dissolution of the salt is accompanied by a large increase in entropy. That's not always the case, and there's some exceptions. But if you think about it, you know, what is more ordered, this lattice or when they become dissociated or dissolved, right? So that's pretty straightforward. The change in free energy is same as this Gibbs free energy formula that we're going to talk about later. But that's just something to think about. I like this little side note. When we talk about dissolving things, you should never say like dissolves like. That won't fly. We have to talk about those specific intermolecular forces, and so we have to talk about with the water here, like the dipole ion interaction between the water and the chloride here. This is a little small for my taste. Maybe it's to scale, but that is going to have to be stronger than the ionic bond here to be able to overcome that and to dissociate it. So think about that. Okay, so here is part of a free response. It's not the whole thing. It's just C, D, and E. But these parts you can go ahead and do. I'm going to say maybe take about 8 minutes for this. Take about 8 minutes and work this out on your paper. looks like most of you guys are finishing. I'll give you a second to do that. All right. You got it though. Okay. So if we take a second to look at this, before you even read the question, you're going to kind of scan over the molecules. What's happening here in this dichloromethane is we have chlorine bonded to carbon, and so in this situation, these individual bonds, these individual covalent bonds are polar, and then CH, those bonds are not. They are nonpolar. So what ends up happening, I have this tetrahedral structure. These dipoles here, it's not symmetric, so they don't cancel out. So overall, this is a polar covalent molecule. What ends up happening here, I have polar bonds between the carbon and the chlorine, but it is symmetrical, so this is overall nonpolar. Hydrogen only has one electron, chlorine has 17. And so if we compare these based on London dispersion forces, the carbon tetrachloride will have much larger or stronger London dispersion forces because it is more polarizable, because it has, 32 more electrons in the molecule. Okay, so dichloromethane has a greater solubility in water. Count for this based on terms of the intermolecular forces between each of the solutes in water. Now, what you have to do is you have to make an argument for both of them. So the dichloromethane has a greater solubility because if it has hydrogen bonds, first of all, you need to mention this. This doesn't have hydrogen bonds, so that's fine. But it will have dipole-dipole interactions with the water, and everything has London dispersion forces, right? So that is what's going to be present between the dichloromethane and the water. The carbon tetrachloride will have only London dispersion forces because it's nonpolar. So we'll see that in the key in a second. In terms of intermolecular forces, explains why dichloromethane has a higher vapor pressure than carbon tetrachloride. Now, when you're thinking about vapor pressure goes against the grain when you're thinking about intermolecular forces. The stronger the intermolecular forces, the higher the boiling point, the higher the melting point. But the stronger the intermolecular forces, the lower the vapor pressure is. You have to recall that vapor pressure is going to be related to the amount of those molecules that are actually in vapor, in gaseous state above your liquid. Okay, so the stronger the intermolecular forces, the less it's going to vaporize. Okay, so anyway, what's going on here? The reason dichloromethane has a higher vapor pressure, that means, like I said, we got to think about weaker intermolecular forces. What's happening? The carbon tetrachloride has a lot stronger IMFs as far as LDFs, London dispersion forces, because it's more polarizable by a lot. And then completing that and adding that water in, we need to make a sandwich. This oxygen has the lone pair here, and I think it just wanted to just draw a water molecule. You're going to get extra credit for drawing 3? No, just draw 1. So the water molecule is going to need to go in this. Oops, I didn't mean to touch it, but there it is. It goes in that area. So here is what I was saying. The CH2, Cl2 is polar, and then Cl4 only has, oh, and I didn't mention dipole and induced dipole, which they're saying or London dispersion forces, so you'd be fine. Remember a dipole, induced dipole, what ends up happening, that's really, if you think about it, that's basically the same thing as London dispersion force. It's the same thing. So don't worry that we said something different. So we already talked about that. And then CH2Cl2 has the higher vapor pressure because it must be weaker than the very strong LDFs. So just because something's polar, that doesn't necessarily mean it has stronger IMFs, okay? If you have a lot more electrons, the London dispersion forces can be quite strong, okay? And then here is your water, and so the hydrogen is going to be an intermolecular attraction with this oxygen. Notice it has the lone pair here, so we're good. And then there you go. I guess if you weren't thinking about it, I mean, I don't guess y'all would do this. I hope you don't. But people may accidentally maybe put the oxygen here for the water. I don't know. Yes, sir.
Wait, so the reason for the vapor pressure being higher in dichloromethane is not because the CCl4 will not like boil as much, right? It's because that the like interactions in the gaseous state of like,
No, so right. It is related to that. Let me go back. If you look at the boiling point, the dichloromethane has a high boiling point, higher, and it has a lower vapor pressure. Those go together. High boiling point, low vapor pressure. So this tells me, like, if I didn't even have this picture, I could tell you right now that the intermolecular forces are actually going to be weaker for the dichloromethane because it has a lower boiling point. And then I would expect it to have a higher vapor pressure, and it does. So those are related. And like I said, if you have a big enough difference in the number of electrons, your polarizability can increase to the point that it actually makes the molecule have stronger IMFs than something that's polar, even though it's non-polar. It's kind of, you wouldn't really be able to figure this out unless they gave you the data, right? And then they did give you the data. So if you have data in front of you, then that's going to trump whatever background knowledge you have, because you do know the actual numbers. Yes.
The LDFs, can we just put LDF or do we have to write out one?
I think you're okay to write out LDF. Yes, you're good. All right. Another question: which of the following substances will have the highest vapor pressure at 25 degrees Celsius? So think, what is vapor pressure versus boiling point, melt point? It's different. Okay. Don't get tricked by that. I think I have my answer. Do you have your answer? All right. So water's polar, has hydrogen bonds. Hydrogen bonds are very strong. Mercury, if you think about how many electrons are in mercury, it's a lot. It's about 80. So CCl4, in that situation, it's nonpolar, and that has less electrons than the mercury, if we're going with that. And then C10H22 is completely nonpolar, but that's a big molecule. So the London dispersion forces there will be quite high. So I think C is going to be your best answer. So anyway, vapor pressure, like I said, it goes against the grain. High vapor pressure means low IMFs. It's indirectly related, not directly related. So here is a picture of CCl4, carbon tetrachloride, and you can tell that, even though all these bonds are polar, it has no net dipole moment because they cancel out because it's symmetrical. If you have something that's tetrahedral out here, like in order for any dipoles to cancel, like you can't just, like these two, like if these two, there's no way to have two of these that are polar to cancel out because of the shape of it, right? You have to, for something that's tetrahedral to be nonpolar, if it has polar bonds, all four of them have to be the same, right? So remember the H2Cl2 from a minute ago, it was polar because you had two nonpolar and two polar bonds, and it doesn't cancel out. All right, bonding and electronegativity. So I don't think that you have to worry about these specific numbers. I've seen some values, say 1.9, whatever. But the deal is, the bigger the electronegativity difference, the more polar it is. And so we're going to have polar bonds. So if you have a polarity great enough, then it will actually become an ionic bond, right? So which of these has the most ionic character? And you actually have the electronegativity values that you need up under the picture. So you can subtract if you need to. Okay. So it's a pretty close call, so you do have to do a little bit of math. You got it? Okay. Whee. So when you subtract the NaF, well, it's actually not that close. You get 3.1. So never mind, I was just kidding. Not that close. Which of these would be the most polar? So if you're having to do this and you don't have the values, then you need to look at the periodic table and think about your electronegativity trends. Remember, as you go down a group, so you go down a single group on the periodic table, your electronegativity is going to decrease because your Coulomb attraction between the nucleus and the electrons will be less. And you know, the period, as you go across a period, your electronegativity is going to increase because you have an increased effective nuclear force, and that is going to pull electrons in a bond more strongly. I know, it's like you have to just keep saying these like long lines. If I say it enough, like, do you think you'll just, spew it out onto your paper? Miss Freeman said. Do you have it? I think I have it. Got it. So H and F, if we're looking on the periodic table, fluorine is the most electronegative element. Okay, so nitrogen, oxygen, and fluorine, the reason they hydrogen bond or are involved in hydrogen bonding is because they're so electronegative. Okay, fluorine is also quite electronegative, but it's a larger molecule, so you're gonna have less Coulomb attraction. Whee! So you get C in this case. Atoms that are far apart on the periodic table will have greater difference in electronegativity. Yeah, that's a good rule of thumb, but I'm going to look closely at stuff as I answer questions like this.
Wait, can we go back to that periodic table to add all that?
Well, sure. Yeah.
I just want to see how electronegative
Hydrogen's around 2. Can't see the second one, but it's either 2.0 or 2.1. Maybe it's 2 point something. Oh, wait. Haha, 2.1. Hey, good job, Miss Bree. I know that. Random facts. Good question. If you remember, we talked about this in class. Ionic substances, they exhibit fracturing when they're hit with a blunt force, because what ends up happening is this is how they're kind of situated in a normal lattice. If you hit them with a hammer, like if you have a crystal, like if I have a piece of halite, which is sodium chloride, and I hit it with a hammer, it will break and it'll actually have a nice plane of cleavage, which it's kind of like the same. Same word there. I mean, it makes sense, but it will cleave or it will break because those light charges will come in contact with light charges and they'll repel each other. So there you go. That makes them brittle. That makes them not malleable for that reason. You can't ductile. They're not ductile, which is to draw something out into a wire. They can't do any of that. All right. Which of the following statements regarding the above ionic solids are true? Oh, they're breaking out the bowling points on us again. You guys got it? Still thinking?
I got it.
Well, are they malleable or ductile if it's ionic ever? No. So as far as having a higher boiling point, at this point we're going to look at Coulombic attraction. So we have apples to apples as far as overall charge. If one of these had something with a 2+ in it, then hey, that would have been the higher boiling point, but we don't. So now we're going to look at size. So with Coulombic attraction, the decrease in the distance is going to increase Coulombic attraction. So substance 1 would have a higher boiling point if we're thinking about that. So that should be C. Well, not C. Yeah, though that is C. Numbers and letters really give me a break. Metals are malleable, and the reason they're malleable is because they exhibit this sea of electrons. So metallic bonds not the easiest type to understand. Imagine filling your bathtub with golf balls, and the golf balls will arrange themselves in an orderly fashion, and you can't really see a whole lot of spaces. And so electrons kind of fill up the spaces between the atoms just the way water would fill up the spaces between the golf balls. And so because the electrons are really shared and they're kind of able to move, that does allow you to, for example, hammer it out and make it malleable or draw it into a wire. And then obviously a flow of electrons is electricity. That's why they conduct electricity. That's also why they conduct heat. So that's and they're not volatile, so they don't metals don't vaporize easily. So which of the following metallic properties is best explained by the sea of electrons? You guys got it?
Yeah.
Yay! We're gonna make a 5, boy. So electrical. Yeah, that's you hope, you wish, right? So here's a series of 3 questions. Good times. I wish you well. Yep. So we're gonna take one at a time. These should go kind of quickly. Oh, do you remember how hybridization goes? Yes, I told you how it goes. Ralph's like, I hate you. It's okay, Callie. I love you. Oh, she wants to do the questions. All right, you go, girl. Got it? It should be kind of a quick thing. So if you recall, okay, the way you do hybridization is you look at the areas of electron density, okay? So an area of electron density, you got to remember a single bond, double bond, triple bond, all one area of electron density. And a lone pair is one area of electron density. So I have 1, 2, 3, 4 areas of electron density around that oxygen. So you just sit there and you count. Just make it simple as possible. So 1, and then I need 3 more sp3. And we don't have to do D. We don't have to worry about the hybridization that goes into the D, so we don't have to worry about that. So it should be C. Yay. Which of the following molecules has polar bonds but is a non-polar molecule? So we just talked about this a little bit. Yes. It's the same exact one. So, it's E. Okay, good for you. Which of the following molecules has a tetrahedral shape? Listen, when you get on the AP exam, you need to draw, and if it's, something you're not absolutely sure about, draw a Lewis structure. So which one would be a tetrahedral? I mean, this one's pretty simple. It's a D, right? Yeah. But listen, too, though, that is the molecular shape. The electron, like if you just look at how the electrons are arranged, that is also a tetrahedral shape for ammonia. Yep. So careful of that. So it is D, but the ammonia, if you look at the molecular shape, what is it? Trigonal pyramidal, but the electrons are configured in a tetrahedral shape if you look at the areas of electron density. So you can do different tests, and there's a virtual lab that you can do for bonding if you need to go back over that. This is sort of at the beginning of the PowerPoint. but we have different things for melting points. Ionic compounds have high melting points and boiling points. Covalents are going to be low, except for giant covalent molecules. When I say giant, we mean network covalent. So that's diamond, that's silicon dioxide, that's it could be graphite. It has a high one. It conducts electricity. I'm trying to think of other network covalent. Those are the two. Silicon dioxide for glass or sand, you know, and then diamonds. Silicon dioxide. Yep. All right. So electrical conductivity. You can only conduct electricity as something that is either molten or aqueous. So the solid doesn't, and they use that a lot, you guys. Covalent compounds don't conduct electricity. Acids can conduct electricity, and they're technically covalently bonded, so they keep that in mind because they do dissociate and deprotonate. So solubility in water and organic solvents. So organic solvents, we're talking about non-polar solvents, okay? So soluble in water and soluble in organic solvents, that makes sense because the London dispersion forces between a nonpolar solvent and the ions won't be strong enough to break apart that lattice. Right? The water can do that. Insoluble in water except for simple molecules, and then they're going to be soluble in organic or non-polar solvents. So not volatile, and then covalent compounds. It says highly volatile. That's not true for network covalent, though, right? They're not going to vaporize easily. Good luck boiling a diamond. I wish you well. Sarcasm. So the properties of compounds help to differentiate them from each other, and so you can click here to do a virtual lab if you need to have more practice on IMS. So crystal structure of ionic compounds. Here is a lattice here, and they are ionically bonded. And so, you know, that's how they arrange themselves. And notice the differences in size. Pay attention to that. The strength of an ionic bond is related to which one? So go ahead and work on this one. This is kind of easy too. You already got the answer? Good for you. There you go. I think you'll know about Coulomb's law on the AP exam. So sodium chloride and magnesium oxide have exactly the same structure. Their melting and boiling points are this, though. So why is that? So this is I want you to talk about this and talk about Coulomb's law, okay? So take maybe 2 or 3 minutes and, you know, write out a response. This is not multiple choice. What I want to do is, I want to finish Big I Did It Too, and then we'll take a break, okay? Got it? So we're going to be referring back to Coulombic attraction. So the charge of 2 minus and 2 plus on the ions are going to be more strongly attracted or have a greater Coulombic attraction than the 1 plus and 1 minus on the sodium chloride. And then the ions for magnesium and oxygen, or oxide in this case, sorry, are smaller than sodium and chloride. So really, the magnesium oxide has 2 things working for it as far as increasing the boiling point. All right, so alloys. Woo. There are 2 different kinds of alloys. There's substitutional, where if we have substitutional alloys, you can see that they're going to be substituted with other metals, or it doesn't necessarily have to be a metal, but other atoms that are similar size. So interstitial alloys, a good example of this would be steel. We have iron and carbon. Those carbon atoms are actually going to get in the spaces, which means interstitial is inside the spaces of the atom. And so what's going to happen with interstitial alloys is that is going to kind of reduce the malleability and the ductility, but it's going to increase the strength. So you want steel to be strong to hold up buildings, right? But we don't want it to bend. So this is good for that. But I wouldn't use this to make it more malleable if I wanted to make, maybe wire or something. So substitutional alloys, like I said, similar size, smaller inside the space. That's interstitial. So go ahead and try this. Pure silver is generally considered too soft, right, to form useful objects, and is generally alloyed with other metals such as copper and gold. Copper and silver is actually what sterling silver is, and so you can actually do a lab and figure out the amount of copper through a precipitate, and so that's something that people do. If copper and silver alloy is harder than the silver gold alloy, which of the following would best explain it? All right, you got it? All right, cool. So we're going to be looking at the radius here. The electronegativity isn't going to really matter, but copper having a small radius than silver, if you look at the periodic table, copper is above silver on the periodic table, so it has 1 less energy level, so its atomic radius is going to be smaller. And so that is the best answer. When they're different sizes like that, it's going to sort of interrupt that structure, and so it will make it harder. And so that's why C is a better answer. So that's why you have sterling silver instead of just silver. Sterling silver still oxidizes. It doesn't have anything to do with chemical properties. So an example of an alloy is shown in the diagram below. Compare with I think it skipped. No, I guess not. An example of an alloy is shown in the diagram below. Compared with the pure metal X, how would you expect the properties of the alloy to vary? So this kind of goes back to the same idea. Take a look at it. All right, got it? All right, so as far as malleability, this one should be less malleable, right? So, but the density, the atoms, this is actually something that people have argued back and forth about as far as like the correctness of it. So But the atoms themselves are in the spaces of element Y gets in the spaces of element X. So definitely going to be less malleable, but it would be higher in density because you have more mass in the same volume. I mean, that's the definition of density. So there's that one. Metallic solids, what's going to happen there? They're not very volatile, so they don't vaporize easily. If we have substitutional alloys here, you can see the copper and zinc, same size. We already talked about that. So, you know, they're going to have delocalized electrons. This is kind of a review of some things that we've already covered. One type of semiconductor, if you recall semiconductors, you have P-type and N-type, okay? You add some impurities can increase the conductivity of a semiconductor. Adding which of the following would increase or create a P-type semiconductor? That wasn't really on the slide. So if you recall, a P-type semiconductor, like look at group 14 in the periodic table. So we have a carbon, silicon, okay. So if I add in phosphorus, right? Phosphorus is actually going to have, you know, one more electron. So that's actually going to create an N-type semiconductor. But if I add in something like boron, then that would make a P-type because it would have one less and that would be positive compared to the silicon that's already present in a semiconductor. Does that make sense? So that's how you're thinking about this. So boron's not a choice. So gallium, yeah. Yeah. So P-type and N-type. When a P-type semiconductor, you need to add a positive ion or a positive atom in comparison to your group 14 things. And if it's a N-type, you need to add something that has an extra electron in comparison. It's pretty straightforward. So covalent compounds, these are, this is what I've been talking about over and over again. Here is my graphite, and if you look really closely, like if I could rotate this picture somehow, you would be able to see that, you know, each carbon, like if I look right here, each carbon is only in 3 bonds, so there are electrons that kind of flow through this area. This is why your pen can write on, your pencil can write on your paper, because there are strong bonds between the carbon atoms themselves, but there's this area of delocalized electrons, and so that flakes off in sheets, and that's why we write with graphite. This is pretty interesting. Now, in diamond, each of the carbons is bonded in 4 other bonds, so there's no delocalized electrons, so it's very strong. And so graphite will conduct electricity, diamond will not. There you go. They're both have really high boiling points because they both have, you know, these. To get this to boil, right? You're not breaking intermolecular bonds. There's no. You're not overcoming IMFs to get this to change states. You have to overcome and break covalent bonds. So that's a lot more energy needed to do that. All right. Diamond has a high melting point and it's extremely hard. Which characteristic of diamond's bonding and structure accounts for these observations? Yeah, sometimes I tell you all the answers on accident before it comes. My bad.
That's it.
It's okay. I would rather be a little bit like, I get it and bored than like I'm completely lost and going to fail. Like if I have to sort that out. So, of course, it's D. Yay! This is an actual AP exam question from an FRQ since they edited the test. So take yourself, take about 2 minutes and do this. You got it? Do you see how these are really, really quite similar? The only thing that's different in polypropylene and PVC is that these methyl groups here in PVC are actually substituted with chlorine. Take a second and look at the mass of chlorine. 35. The mass of a methyl group, which is a carbon and 3 hydrogens, is going to be 15, right? So the one that's a methyl group, not methane. Yeah, so it's only 15. Anyway, the reason that, and this is that means it gets repeated, so there's, a big difference there. So the spacing is similar. The ones that sink are going to be made of PVC because they're going to have a larger mass in the same volume because it said the volumes are similar. Okay, so density is mass divided by volume. Ta-da! And so again, that's the definition of density.
Yeah.
You got any questions? You good? Okay, so molecular compounds, there are different kinds of molecular compounds. Polar covalent, they're going to align themselves with dipole-dipole interactions. And then, of course, hydrogen bonds are a special kind of dipole-dipole, so this is actually a hydrogen bond. So anyway, iodine is a non-polar covalent, and it's actually, we call that just a molecular solid. This is molecular solid. The only thing that's making it a solid is that it has so many electrons that it's very polarizable. If you look at the periodic table in group 17 of halogens, like fluorine and chlorine gas are gases. They're red on your periodic table, and then bromine's a liquid, and then iodine's a solid. And the reason that happens at room temperature is because fluorine and chlorine are the least polarizable of group 17. So they don't have enough London dispersion forces to create strong enough temporary dipoles to make it a solid. Yay. Anyway, so if you remember, we did the iodine and we heated it up and it made this beautiful purple, sorry, it's sublimed. If you looked at it, it did make a liquid for a minute, so maybe it just boiled and then, vaporized, but melted and then boiled. But what you have there, you just have the London dispersion forces to overcome in order to change states. So, which of the following bonds are broken when water boils? Or not bonds, which are the following, excuse me. Which of the following are broken when water boils? This is a really commonly missed thing. People think that covalent bonds are broken when water boils. No. 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 You don't break bonds when you boil water. The energy needed to break a covalent bond, it ain't coming from your stove and your water. Sorry, no. Explain why iodine is a solid with a low melting point and mostly insoluble in water, but soluble in organic solvents such as hexane is also a non-conductor of electricity. I think you need to take yourself on that one if you haven't already started on it. Go ahead and take a couple minutes, like 2 minutes. This is a really good example of an FRQ that you might have to answer. So take about 2 minutes on this one. So you have several things to address here. Feel like you got them? Okay. Great. All right, so iodine is just I2 molecules, and so the only interactions between those. Look, do you see where it says van der Waals? You don't say that. I never taught you that, but don't say that. You say London dispersion forces. Do you hear me? No. Okay. There are enough electrons in the iodine molecule to make temporary dipoles, so it's polarizable, and so you got the London dispersion forces going on there pretty strong. It is insoluble in water because the only attraction between water molecules and iodine molecules are London dispersion forces. So here's the thing. Iodine's London dispersion forces with water are not strong enough to overcome the hydrogen bonds in the water to become dissolved in it. You have to be able to say that. Okay? It doesn't, oh, it's not polar, so light dissolves. Like, no, you don't say that. So that doesn't have, like I said, in order to get the iodine molecules in between the water molecules, you'd have to break the hydrogen bonds in the water, and so that's not going to happen. Very few, if you think about, the kinetic energy of those particles, most of them will not have the energy to do that. It dissolves in organic solvents because in order to dissolve in an organic solvent, they would just have to overcome the London dispersion forces in the hexane, which can be done. Okay. Iodine doesn't conduct electricity because it doesn't have any localized electrons. It doesn't have any electrons. It doesn't have charge. It doesn't ionize in water or anything like that. All right, so there is Big Idea 2. We're going to start Big Idea 3 when we come back from lunch, which will be around 12:45 or 12:30. 12:30? 12:30. 12:30. We'll catch you then.
I believe like an hour.
We'll take 45 minutes. Alright, is that PowerPoint still in the window it's supposed to be in? Hopefully it's still back there. Okay, cause I can't touch it, right?
Wait, Fred, are you recording these too? And posting them afterwards?
Yes, so what I'm doing,
You know the stream will stay on your channel, like the video will stay up there after you're done. You don't have to post it.
oh, I know that. I know that. So what I'm doing is, I am,
Oh my god. You're hurting all of our heads, is what you're doing.
alright, it's time to go. Okay, I'll wait another minute, actually.
It's like a pier. It's like a pyramid. Yeah.
What's this key go to? This is the master key.
The master key. No. Okay, let's get. Oh, I think I'm already streaming, aren't I? Did I?
Yeah.
Oh. All right, let's get started then. It's time. I'm actually gonna whatever you want. All right, here we go, guys. We're gonna get started with big idea 3. So chemical reactions. So that nice little particulate model is a good indication of what's about to happen to you. Kind of expand some ideas from big idea 1 as well. I say that. I don't know. There we go. So obviously we're going to rearrange and reorganize the atoms and elements. There are different kinds of chemical reactions. Combustion, acid-base, which is neutralization, oxidation, reduction, and precipitation. Remember with oxidation and reduction, we're going to have a transfer of electrons there. Combustion, we're going to take a hydrocarbon, combine it with oxygen, and get water and carbon dioxide. So that's just some basic stuff. And then as far as talking about basic stuff, this is going to come back, that's going to come back in big idea 6 with acid base. So we'll get to that shortly. When we're writing net ionic equations, which a lot of times when you have a free response and it starts like this, you can get an easy point from writing a net ionic equation. So here's an example of that. And so when you're doing this, you want to think about what is actually being involved in the reaction, what is actually going into making products, and what doesn't really participate. Okay? So go ahead and take about a minute to write this net ionic equation. If you're struggling to get started, look at the Ka for this acid. It's a weak acid, and so you got to think at equilibrium. Mostly that this form of it will be present, right? It won't be deprotonated at equilibrium. So think about that as you write the net ionic equation. This one's a little bit different than maybe what you're used to having to do, but all the information you need is there. You guys got it? All right. So you guys, as you look at these two reactants, you should know by now, hopefully, that potassium, sodium, lithium, those are typically going to be spectator ions. So this potassium is not going to go into forming your sorbic acid, and then this chloride ion, when I put hydrochloric acid into an aqueous solution, that chloride ion is also going to be a spectator, right? So we're basically, when you look at it, we're going to be forming that sorbic acid. That one's kind of tricky. Like you might struggle with that more than you might struggle with writing a net ionic equation for something like a precipitation reaction, right? Anybody got any questions on this one? If you struggled with that, the big piece of information that you needed was right here, that this is a weak acid. So like I said, at equilibrium, you will have in solution, most of your sorbic acid will remain protonated. It won't get deprotonated. It will be like this. Any questions there? Okay, so that was one point. Going on, if you have trouble with net ionic equations, you can always write the complete, and then the complete ionic, and then the net ionic. But the free responses are, timed, and you have a lot going on. So hopefully, you're at this point can just ask yourself what actually goes into making a new substance, and if it doesn't do that, then don't. So spectator ions should not be included in your balanced equation. Remember, the point of a net ionic is to show only those ions that are involved in the reaction. And so you only need to memorize the compounds like nitrate, ammonium, halides, and alkali metals. Those are soluble. So there used to be more solubility rules. Those are the only ones that you need to know. And if you recall, I told you guys that nitrate, right? We think about our cheating little tips for nitrate. Nitrate is no, right? Does it form a precipitate? No, like 3 O's, right? And then ammonium, so that's NH4. And then your halides, those are pretty simple. And then alkali metals, you got, nah, they don't make a precipitate. So anyway, moving on from that, pretty straightforward. So here's a good question for you. Solid copper is strongly heated. Solid copper carbonate is strongly heated. So try to make a prediction about what that could form. If you don't know what that could possibly do, this one is gonna break down into copper 2 oxide and carbon dioxide. I don't know that they would expect you to necessarily know that it would break down into copper 2 oxide and carbon dioxide. I don't think that level of prediction is still on the test. It used to be before they revised it, so don't stress too much about that. I think the rest of them, though, you can go ahead and do. So take yourself about maybe 4 or 5, maybe about 5 minutes. Does everybody remember the formula for percent yield? Is that ringing a bell? Nope. No, actually that's not right. Actual over theoretical yield. So it's actual yield divided by theoretical yield times 100. And that's not on your formula sheet. So you can remember, to help yourself, you can remember at. Actual, oops, I thought I hit the pen, but I did not. You can remember at. Actual divided by theoretical times 100. At, okay? And so this is something that we need to know. So take about 5 minutes to complete. This has a little bit of math, and it's a free response, so you can use a calculator, obviously. Take yourself a few minutes and work this out. See a couple people finishing up. If you're not quite finished, you can have another minute, maybe two. How we faring? As some of you guys finished, remember the actual yield is what you actually got in a lab. A theoretical yield is what you theoretically get on paper. So stoichiometry tells you theoretical. The actual yield, let's say, was retrieved or was massed or something like that. Can I move on? Yep. All right, so let's do that then. So if we heated this, we would observe gas being evolved. The color change, like I said, would you know the color change off the top of your head? No, and they don't expect you to. What is the percent yield? So the theoretical yield, you would start with the 10 grams of copper to carbonate, and then you would go to moles of copper to carbonate, and then be able to convert to moles of carbon dioxide, and then here's your molar mass of carbon dioxide, and there's your grams. So again, percent yield is actual divided by theoretical times 100. The correct sig figs actually, it is 90, but you would have to put a decimal there or write it as 9.0 times 10 to the first, because you have 2 sig figs right here, and if you think about it, that's only 1 sig fig, right? So watch your sig figs. And the sig figs, when you see those on the FRQs, they're going to be related to the questions that are lab work that involve using data or instruments. So this would be an example of a time that would, I mean, you should always watch your sig figs, but this would be an instance that it would apply to. How could you improve your percent yield? You could reheat it, see if there's any further mass loss, right? And anytime you're drying something or heating something and making a product or massing a product, if you can repeat something, then you should until you stop seeing a change in the mass, okay? Make sure you have pure copper 2 carbonate. It doesn't have any contaminants in it. So, any questions there? Do I need to, I see you guys writing some things down. Do I need to work this out for you? No? Notice there's only one reactant, so we don't have to worry about is that a limiting reactant or not. If we had 2 reactants, then we might want to make a BCA table in this situation because we've had to find a limiting one, right? So, oh, look at here. Oops. So listen to me. When you're given the mass of 2 different reactants, it really is at your, it's to your benefit to go ahead and make yourself a BCA table to identify the limiting reactant. Because notice in subsequent questions, they will ask you how much is left over, what's remaining, or it could be based on a particulate kind of thinking where you have to talk about the molarity and stuff. So if you go ahead and do a BCA table, you have all the data that you need in subsequent questions. I have a little bit of a trouble writing this in a BCA table to size. I may take your molar conversions and use them just so I can fit everything. Yeah, I'm gonna have to scooch down, I think. Have you guys already successfully converted these to moles? Good, you already did that? Good. So I'm just gonna quietly do that while you're doing it on your paper. The molar mass of aluminum sulfide is gonna be 2 aluminums and 3 sulfurs. So I got 150.14. Just to save time, what is the number? We're going to convert the moles to moles of water in the same manner. What is the? Is it just 10 divided by 18, right? It's the 18.02. Did you get 0.555 moles? Okay, great. I can't erase. Just right over it. I'll make that a 5. No, I don't think I can.
You made the bottom half of
Yeah, so 0.555. There we go. That looks great. So beginning in your, I can maybe change the color a little bit. There we go. That's a 5. All better. So beginning for the table here, we're going to have 0.0999 moles of aluminum sulfide and then 0.555 moles of water. Now, we can't just look at that and say which one's limited in excess because they don't react in the same ratio. So, for every 1 aluminum sulfide that reacts, see my coefficient here is 1, I'm going to have 6 waters react. And so this is going to be 2 aluminum hydroxides getting formed and 3 hydrogen sulfides getting formed. So what we're going to do to determine which one is a limiting reactant, whichever one has the smallest X value is a limiting reactant, okay? So in this situation, X is going to be equal to, I mean, you can just eyeball that, to be, if I use it all, right? If this is a limiting reactant, it's going to be completely consumed. And then if I solve for X in this situation, if you think about this one, if I write it out for you, to solve for X, it would be 0.555 equals, I think I mixed that up. Excuse me, 0.555 minus 6X equals 0. And so in this situation, to solve for X, I'm going to need to subtract by 0.555 and then divide by 6, negative 6. So 0.555 divided by 6. So in this situation, X is equal to 0.0925. So which one's the limiting reactant, water or aluminum sulfide? Water. So water is the limiting reactant, and so X is equal to this. Okay. If you put this into this X, you're going to get a negative number, and then you can't have a negative amount of water. So that should be your big clue that I did that wrong. So X is equal to 0.095. So now we can just do fun little math and fill in the bottom of our VCA table, and those would be the number of moles of all these. So I'm just going to do all my subtraction. 0.0999 minus 0.0925 is equal to 0.0074 moles of aluminum sulfide. In this situation, 0.555 minus 6. Oh, we already know this one's Limiton, so that's going to be 0. We already solved for that. To find the moles of aluminum hydroxide made 2 times 0.0925. So this is 0.185 moles of aluminum hydroxide. And then the last one, 3 times 0.0925. I got 0.277. I'll make that 7. 2775. So 0.28. I'll just go with that. So those are the amount of moles that I have of each that were formed. So for my sig figs to be correct, if you look at what you're given, these should all have 4, so I can do that if I need to. That could be 0.2775 if I want to keep it that way. What?
Did you add too many zeros to that?
This has 4 significant figures now. These are not significant. Only trailing zeros when the decimal are significant. These are placeholders. That's a good question. So correct sig figs on this one would be 0.2775 moles. So that's kind of what happens. So the limiting reactant is water. Now notice on B, what is the maximum mass of H2S? All you're going to do to solve for that is you're going to take the moles and then multiply by the molar mass, and we'll see that. And then how much is left? We can also convert that back to moles. So here's all the work. No matter how you do this, I know the BCA table is like a lot of work. It's work no matter how you do it, okay? So to me, I'd rather do a BCA table and then have everything laid out in front of me. Then I can easily look at that bottom line and see what I'm left with, okay? So H2O is limiting. And then, like I said, you can take the moles, which is what they get here, and if you multiply by this molar mass, so H2, if you take 0.2775 and you multiply by 34.09, 0809, you will get that much, that many grams. And then how much excess? You can do it a couple different ways, but to me, all you have to do is take this after and multiply it by the molar mass. So you're going to get the same answer, but I would just rather, like I said, have it all graphically. Yes, sir?
Is it wrong to leave that, like for C, if we had it listed in moles?
On the AP exam, it'll tell you in grams, and you'll know.
Okay.
But sometimes it does leave it at moles. Sometimes it'll say how many moles are left. So you just got to be careful. But yeah, you need to do whatever they tell you. And it didn't really, to me, wasn't specific here, but they will be specific on May 1st. Okay, I feel like we just did this. Oh, they used a BCA table. That's nice. Great. Some people that helped make this PowerPoint, they liked BCA tables, and some people didn't, so they went in and added that in. So this is what we got, right? Okay, cool. Yay. All right, so synthesis. A sample of pure copper is heated in excess pure oxygen. So notice here we can already tell that the copper is the limiting reactant, so we don't necessarily need to solve for that. Copper's going to already be there. Design an experiment to determine quantitatively whether the product is copper 2 oxide, or I guess that would be copper 1 oxide. So if we look at some of those steps, what could you do? So you could find the mass of the copper, and you could heat it and heat an oxygen to constant new mass. So that's the same idea where you need to repeat it until the mass stays the same. Okay. So trying to find the mass of the oxygen that combined. Here's the deal. If you think about it, gonna give you something. Well, the amount of copper you came in with is not going to change. Like these copper atoms will not be created or destroyed, right? So when you mass, like if it's CO or if it's Cu2O, the amount of copper, we have to bounce the equation if it's the Cu2O, right? But, well, we need to bounce it either way. It's not balanced. But whatever number of coppers go in has to equal what comes out. So the change in mass will be due only to oxygen. That's kind of complicated, right? I mean, it's easy to think about now. You're gonna find the mass of, like I said, find the mass of copper, and you'll be able to, for example, let's just say that we formed, 17.12 grams of copper oxide or copper 1 or copper 2 oxide. We could subtract the original mass of copper and go to moles and then find the moles of oxygen, and then you'll know if it was a 1-to-1 ratio or 1-to-2 ratio. Okay. The second one, decomposition here, design a plan to prove experimentally that this reaction illustrates conservation of mass. So why don't you take a second to do this one on your own? Like, what could you do if you were heating calcium carbonate into a solid and a gas? How could you prove that the law of conservation of mass was holding true here in this situation? Do you have some ideas? Yeah. So you'd obviously need to find the original mass of the calcium carbonate. If you could have this in a rigid container and seal it, you could, we don't have this, but you could evacuate the container. It's a little bit more high-tech than us. We actually have those gas tubes where we can collect gas over water. So that's what we could do. And then you would be able to find the volume. We did that lab, right? We found so we found the volume of the gas, and then you can use PIVNERT to figure out the moles of carbon dioxide. So I don't think that the AP exam would be this open. They may give you some lab equipment. They may give you some stuff. These are really open-ended, but just some things to get you thinking. So data analysis, woo! When tin is treated with concentrated nitric acid, the resulting mixture is strongly heated, and the only product remaining is the oxide of tin. A student wishes to find out whether it is tin oxide or tin 2 oxide or tin 1 oxide. So this is similar to the ones we were just looking at, but it's actually got some data, which I like, because you now have something to work with. The other was just kind of, for instance, so this is the mass of the pure tin that you started with. This is the mass of the crucible. So remember, the crucible is a nice little teacup, not really, but it's the porcelain heating dish that we use for like the hydrate lab, for example. So the mass, here's this, and here's the mass after the second heating. And notice the mass after the second heating and the third heating are very similar, so they know that they don't need to do a fourth heating, okay? How can you use this data in the law of conservation of mass to determine the formula of the product? So I think that they actually go through the process. Close your eyes, don't look. Yeah, they do. So actually, why don't you go ahead, don't just say how to do it, but go ahead and solve for the actual formula. And if this looks really complicated, like I have no idea how to do this, you have masses, you need to go to moles, and if you'll go to moles, your heart will lead you along the way. Your heart will guide you. But really though, when you're solving for formulas, that empirical formula, do you remember the poem I told you? Percent to mass, mass to mole, divide by small, multiply to whole. Anytime you're solving for any kind of formula, that's the answer. So in this situation, percent to mass, mass to mole, divide by small, multiply to whole. And then you're already going to have masses, so you don't have to take percentages. Like you already got your grams. But go to moles and then fill it out with that poem, and you'll get it. I believe in you. I'm not sarcastic. I think you got it. This is going to take you a few minutes, so stick with it, okay? sure of these three masses, which one are you gonna use? The third one. The first two are not helping you, so don't let that drag you down. Yes, ma'am.
I don't know what nitric acid is.
Do you need to know what nitric acid is? No. What that beginning part, nitric acid, by the way, is HNO3. If you ate an acid, it would be icky. So nitrate is nitric. Okay. But this question is asking what the formula is. Is it SNO or SNO2? So all you need to think about is that second reaction where you heat it in oxygen. And you don't even really, what you need to do is you need to get your moles of tin and your moles of oxygen and divide by the smallest one and get your ratio. So I think you're trying to go back too much. You don't need all that information that you're trying to get. As y'all are kind of cooking on this, ha ha ha. No, not funny. I'm gonna do a little bit of scratch work up here too, so you'll have something to go with.
You divide the smallest into the
Mhm.
other one, right?
Yes, percent to mass decimal divide by small. Yeah. And then multiply to whole. Hopefully you shouldn't have to do a whole lot of multiplying. Oh, this isn't copper, this is tin. I think I was thinking of that last one. Sorry, not trying to freak you out. JK. There you go. Are you stuck here? Anybody stuck here? No? Good. I did it again. There we go. Let's make it a S. That's cool. I see a couple people writing, but some of y'all have stopped. Okay, so at this point, I have solved for the grams of oxygen, and like I said, the grams of tin, the tin didn't go anywhere. As I let it oxidize, it didn't go anywhere. So the mass of tin should be constant. So now I have the mass of tin, I have the mass of oxygen, I'll convert them both to moles. Like I said, you know what to do? You have some masses go to moles. A lot of times on FRQs, that's a point right there, just go to moles. But when you get to moles, percent to mass, mass to mole, divide by the smallest one. So in this situation, I'm gonna guess that the smallest one, I don't know if eyeballing it, I can't really tell. But which one ended up being the smallest one when you went to moles? They're the exact same number. So guess what the formula is? If they're the exact same number, when you divide, they're exactly the same. Your ratio is 1 to 1.
I guess that begs the question. Whenever you
go from moles of oxygen, like grams of oxygen?
It's all, okay, when you're solving for the formula,
Yeah.
then it can be a single oxygen because it's going to be bonded to something, so it's okay that it's not O2.
Okay, so I
Yeah.
I use
That's a good question. A lot of people will ask me that. When you're doing formulas, yes, I know that oxygen in a reaction has to be diatomic if it's alone, but in this situation, you are solving for what the oxygen is bonded to. So by definition, it is not alone, and so it doesn't have to be diatomic, and you should only use 16 grams in one oxygen.
So it's not the same.
So it's
They're
not
not the same. Yeah.
So they're not the same. You were just kidding. Okay, so it's not the same. Cool. So here is the mass of the tin, and there, if you go to moles, there it is. And so, subtract the mass of the crucible. I did that. There it is. Okay, and then calculate the moles of oxygen atoms. So we are using the mass of 16 grams per 1 mole of oxygen. You don't do O2 here. If you do O2 here, you're gonna get the right answer. That's a good question. People always ask that in regular and honors chemistry and AP chemistry. So anyway, notice here that the smallest amount of moles is the 0.0438, and so that the 10, right? Divide both of them by that, and I'll find this divided by itself is 1, and then this divided by 0.0438 is 2, and that's how you do it. So these formulas, I mean, just the little poem I told you is for empirical formula, but any kind of formula follows that same suit. Okay. That one's tricky, huh? Good times. Bronsted-Lowry acids and bases. Bronsted-Lowry, I just think about these being two guys and they're playing like catch with each other, okay? And so if Bronsted-Lowry, right, the acid throws the ball and then the base catches it. And if you look up here, your acid and base, we're going to have a conjugate acid and a conjugate base. And so what I like to think about as far as keeping this straight, if you pair these up, if you have an acid and a conjugate base, like you need the letters A, B, and C. And so here I have a base, and it will be paired up with the conjugate acid. And they'll have, do you see what I'm saying? Conjugate base has a C and a B, A, B, C. You should have the letters A, B, and C when you pair this up. It is a very common question to see just on a multiple choice real quick. What is the conjugate base in the reaction or whatever? So this is an easy point to get. So hydrogen fluoride or hydrofluoric acid in water, it will make a hydronium ions. That will be your conjugate acid, and your conjugate base will be fluoride. Recall that hydrofluoric acid is a weak acid, so the fluoride ion will actually is a relatively strong base, and it will raise the pH at equivalence if we're titrating HF. Might as well get in all the review we can. Do y'all remember that? HF, hydrofluoric acid, is a weak acid, while all the other binary acids with halogens are strong. And the reason for that is because fluoride or fluorine is so small that the Coulombic attraction between the H and the F cannot be overcome by the ion-dipole interaction with the water. Not ion, but the dipole-dipole interaction with the water. Isn't that fun? Don't you just love when I start talking about IMFs? Your little faces are so sad. Anyway, ammonia's conjugate base is, conjugate acid is ammonium, and then there's your water. Its conjugate base is hydroxide. Amphoteric, that just means that water can act as an acid and a base because water can lose. Like if you donate protons, then you're an acid. So it can lose the hydrogen proton here and become hydroxide, or it can take that hydrogen proton and become hydronium, and that acts as a base because it accepts the hydrogen. So this is actually, if we think back to what we talked about with weak and strong, or weak acids, strong acids, this is what happens when an acid is deprotonated, right? This is the hydrogen that is removed. Good times? Having fun? So let's go ahead and, let me erase that a little bit. Let's go ahead and do this. A student designs an experiment to study the reaction between sodium bicarbonate and just acetic acid. So this is a good old volcano from the 3rd grade with some terrible math. I'm just kidding. The reaction is represented by the equation above. A student places 2.24 grams of sodium bicarbonate in a flask and adds 60 milliliters of 0.875 molar acetic acid. This The student observes the formation of bubbles, and the flask gets cooler. Identify the reaction represented above as acid-base, precipitation, or redox, and justify your answer. So you can see kind of where this is going to go. It starts out real chill. Lucky, it gets colder. That's a joke. But it starts out okay, and then it gets worse. So lucky for you, you just have to do that first part. Notice it says justify your answer. So that means you need to give your answer and then clearly explain exactly how you arrived at that. You can use mathematics to justify your answer if you're doing math, but we're not. So you need to be pretty explicit in explaining what you mean. See a lot of different ideas going on. That's fine. And this one's not the most straightforward question, so if you struggle with it, it's okay. Have you at least made a good, solid attempt? Right? So here's the deal. Did you guys see as you were looking at this that this acetic acid right here becomes deprotonated, and then you struggle to find what accepted it, right? Is that what happened? Okay. What is an acid-base reaction, or acid-base reaction? So what ended up happening? Not bicarbonate. I'm getting there in a second. The acetic acid reacts with the weak base bicarbonate, and so it donates a proton, or it's acid-base. No, if you couldn't figure out where it went, you could have said it's an acid-base reaction, no solid precipitates, so it's not a precipitation, and none of the oxidation numbers change. So I saw a couple people doing oxidation numbers. By the way, neutralization reactions, there is no transfer of electrons, right? So there's a transfer of protons, right? So if you do any kind of neutralization reaction, you check the oxidation numbers, they don't change. Okay. So that's just fun facts. But you need to, if you identified it as acid-base, you got a point, even if you couldn't figure out what was going on. But if you took the time to do the oxidation numbers, it says to justify it. So let's say you did all the oxidation numbers. Instead of getting frustrated and erasing it, you could have said, those solid forms, and then the oxidation numbers change, and so that's how I know. And so that's fine. You just have to back it up. But recall, I think that bicarbonate kind of threw you guys off. So this is that's a weak base. You know what's a weak base is because it's we have carbonic acid, right? H2CO3. That would be the conjugate base of carbonic acid. So the formation of this gas, like it doesn't follow suit like exactly the way you want it to. Carbonic acid breaks down into carbon dioxide and water. So I feel you. If I said it like that, if I said that carbonic acid breaks down into carbon dioxide and water, like when it hits water, like that probably would help you. Maybe that's a little tricky, but there you go. So redox reactions, electrons are transferred. That's a redox reaction. When you have something reduced, the red part of redox, it gains electrons, and so that's your little oil rig thing. And I had brought that up to you guys earlier. Oxidation. Oops, my bad. Oh, don't look. Close. Avert your eyes, children. I was just trying to point to the board. Oxidation is losing electrons. If you look at this little oil rig picture down here. And then reduction is gained. There we go. So you may have a difficult time with this definition, and there's a big paragraph that keeps going. For me, what I like to do is I like to just, there we go. I like to think about reduction, reducing the charge. So oxygen here is neutral. It has no, it's not neutral. I should have said its oxidation number is 0. And when it's reduced, its oxidation number goes down. To me, all the little acronyms in the world are great, but you know, if the charge goes down when it's reduced, I like that. That makes a lot more sense to me. So oxidation, the charge gets reduced. Reduction, the charge gets reduced, and oxidation, the charge increases. You go from 0, the oxidation number goes from 0 to 2 plus. So anyway, that I like that better. Redox reactions involve the transfer of electrons, and these half equations show what actually occurs. And so when you have half equations, when you take a redox reaction and you write the half equations, you write a half equation for reduction and a half equation for oxidation. So anyway, no problem there. And you can actually see here oxidation is loss, and you know that already. In this oxidation half reaction, you can see, you know, it loses those electrons. And the reduction is gained. There it goes, gaining the electrons. All right. Those half reactions are not balanced because they don't have the same number of electrons. So if you are writing the half reactions, you notice here that this has to equal that. So you would need to do a little bit of extra work to balance those. It's not quite finished. All right, so good times. Zinc ions will react with aluminum metal according to the following chemical reaction. Based on this chemical reaction, how many moles of electrons would be transferred when 1 mole of zinc 2 ions are consumed? So do you see the moles of electrons there? Do you remember how I told you in the last one it wasn't balanced? So your number of electrons gained is the same as the number of electrons lost. So you would need to do a little bit of work to figure that out on that last one. So go ahead and get that going. I don't think this question actually requires that you write half reactions, does it? No. Okay, so don't do that in this situation. Ooh, can I read? I may need to retract that statement. Start solving and see what you think. Can you eyeball this and tell how many electrons are getting transferred? How many? 6. Right. Yeah. So I think you're good not to write the half equation. type reactions. So if I'm only putting, are y'all finished? Have you kind of sorted it out in your head?
Tell easily of how many elements.
Yeah, I don't understand. How do you know the 6?
Oh, okay. So, if we look at the, you may want to write the half reactions. I don't know if it would be more efficient. It's already balanced, so that tells me that that's kind of sorted out at this point. If they gave you just aluminum and zinc, then maybe you'd have to keep working on it, but that's already been figured out. Anyway, the oxidation number, here we go. The oxidation number of aluminum is 0, and the oxidation number on the zinc is 2 plus, and there's 3 of them, so it says 6 plus charge overall, or overall if you look at it like that. And then this goes to 2 times 3 plus, and this goes to 0. So how many electrons got transferred if it goes from 0 to 3 plus, and there's 2 of them? 6 electrons, right? So 6 electrons were transferred. They already to get these coefficients in this situation. What they did, they already wrote the half reactions and figured that out. So if I only have 1 mole of zinc reacting instead of 3, that's 1/3, right? So how many electrons is that going to be? Just 2, right? So this isn't a big deal. You do have to kind of fill out the situation and see how much work you need to do. Redox titrations. This was something at the end of the semester. Unfortunately, I don't think we did this titration. We talked about it, but we had done several other titrations. So this one is kind of a classic one that most people do. What they do is instead of titrate, you can titrate for a number of reasons. It doesn't have to just be acid and base, but potassium permanganate is this really this color. It's the color of this PowerPoint. I think this PowerPoint is an ode to potassium permanganate. But you can determine the concentration of an unknown analyte by measuring it against a standardized titrant. And so, common example is using a standardized solution of potassium permanganate, which is this right here. Right, there we go. So there's my potassium permanganate, and so you would know the molarity of it. And remember, this is my titrant. It's going to drip down like little ants, and this is what I'm analyzing, so it's the analyte. So I wouldn't know the concentration of this. And so here, if you look at the net ionic equation, that potassium is a spectator ion, right? And then we will find the concentration of iron 2 ions. So in this case, potassium permanganate is a titrant, and it's really useful because it's its own indicator. You can see that it starts out bright purple, and this is clear. And then when the iron 2 solution, when you start, is colorless, and it's possible to tell at the end point because when you have unreacted potassium permanganate, once you have extra potassium permanganate, this will stay pink. While it's getting consumed, though, in the process of getting consumed, it will stay colorless. So you get to the end, you'll have that. The reason this turns pink is because anything that's unreacted will keep this solution pink. While it's reacting, it stays clear. So that's kind of how it works. And here's your net ionic equation here. And this is, you can tell it's a redox reaction. The iron goes from 2 plus to 3 plus, so it gets oxidized because its charge goes up. And then if we look at the oxidation number of manganese here, I believe it's 7 plus, and it goes to 2 plus. So the manganese actually gets reduced. So it's a redox titration for that reason. That's soaking in. The oxidation number of hydrogen doesn't change because it goes from 1 plus, and then in water it's also 1 plus. So it's just the iron and the manganese change in there. All right, we look at this one. We have different evidence of chemical changes. This is pretty standard stuff. Chemical changes, you can have a production of a gas, formation of precipitate, change of color, production of heat. And so they can also absorb heat, right? If you feel something and it feels, quote, feels colder, that is actually an endothermic reaction, similar to the one on the FRQ we just looked at with the sodium bicarbonate and acetic acid. Physical changes can have similar evidence. For example, water that boils makes bubbles. And I put PowerPoint when I made it. I put this in here so you can see that when water is boiling, you're not breaking bonds. You're not making a new substance. You're only breaking or overcoming, I would rather say. You're only overcoming those intermolecular attractions, so the hydrogen bonds, the under-dispersion forces, etc. It is common misconception boiling water makes oxygen gas and hydrogen gas, and that is not true. You don't do that. You're laughing, but I mean, when I teach regular chemistry, I get people, to draw that, and people will draw hydrogen and oxygen. So it's not, there's not enough enthalpy present in your your saucepan to break those covalent bonds. I promise there's not. I'm glad y'all think that's funny. That makes me happy that you understand something enough to laugh. What?
It'd be so bad.
That would be so bad, yes. Chemical reactions involve the formation of new products, bonds between atoms or ions, and bonds always must be broken. Bonds being broken here is always endothermic. Like, it doesn't matter. To break bonds, you have to think about bonds as like, it is an electrostatic attraction. Think about it like magnets. To separate magnets, you have to put energy into that, okay? When bonds are formed, that's going to be like two magnets that want to come together. When they come together and hit, they're going to release energy, like they're going to release sound, right? So that's always exothermic. Now, what ends up happening is sometimes when you have exothermic, the energy needed, the activation energy, and the energy needed to break the bonds is actually less than the energy released when they're formed. And so you'll have energy that's released, and that's exothermic. And then in endothermic reactions, this is going to be a situation where the enthalpy needed to break the bonds is greater than the energy needed, the energy formed when they, the energy released when they are formed. There we go. So that's just something, and we're going to come back to these little reaction pathways later. Okay, so it's been a hot minute since we've done galvanic cells. This is something we did in like December, right at the end of our semester, and it's actually in Big Idea 3, so it's kind of mixed in with some of the earlier ideas from the semester. Now, let's take a look at this. The following question is based on combining the three different half cells listed below. So we have three different half cells, and if you remember, when we write down equations, we have, they're always going to be standard reduction potentials, right? When you're given the reactions for making a cell, they're always going to be reduction. And so if you look at all these are all getting reduced. Now, are we going to make a galvanic cell? We're going to make like a little battery out of a bunch of reduction things? No, we can't. So it's a redox reaction. We have to have something getting oxidized. And remember, the thing with the highest reduction potential, it has the highest potential for being reduced, so it's going to be the thing that gets reduced, right? Am I ringing some bells there for you? This is kind of like when you remember when you're in elementary school and you're in a gifted class and you have to mess around with stuff. That's what this is. So you can tell, like for example, in half cell 1 you have 10-2 creating 10. Well, like this one's reversed, right? So it's been reversed. So this is some like algebra and funness. So I wish you well. I'm going to give you a couple minutes to play around with it, and of course I'll talk about it. I'm going to start doodling some stuff on my paper. This is like what combining equations in algebra. Do you know what I'm talking about? Yeah, you're like, no, I don't want to do math much.
this is the one where you don't, like, multiply, right?
Right, so remember, yeah, if, in this situation, when you're, when you multiply, like, to get the, amount of, electrons bounced, you don't multiply the voltage, right? It's an intrinsic property, or intensive, I think that's the word. But yeah, you don't, I think that's it, yeah, intensive property, you don't multiply. Yeah, so as you're solving, like the fact that there's 2 silvers in the first one and there's 3 in the second one, and cell X versus cell Y, that doesn't change the voltage, no. You got it? Okay, cool. This one's kind of tricky, so don't be sad. The answer is B, so they're going with 0.6 volts. So the potential cell of Z can be calculated. Like I told you, this is kind of like a combination of equations, combining equations in algebra. So if you recall, I think it was the 2015 FRQs had something similar, but it was a little bit easier to follow as far as like getting everything to cancel out. So let me get my pen and pick it up, and I can kind of point you through it. So to find the cell potential of Z, okay, this one right here, what they did was cell Y, if you reverse it, that's going to change its potential from 0.94 to negative 0.94, and then the reactions in X and reverse X and Y will combine to give you Z. So if you look, if you reverse the first one right here, I can rewrite it for you. So let me kind of write it up here. If I take this first one and I go SN2 minus plus 2 silvers, and that's a solid, so it's not the same, and it'll give me 10 and then 2 silver ions. So if I kind of add that together, well, I do need to multiply a little bit, but you can see that we end up with the chromium here, and my silver, it looks like the silvers end up canceling.
They
Trying to
just have to combine.
just combine them, right? I'm looking at that silver though.
Let's just do the flip of it.
Yeah, you do. You reverse that one, and they give you Z. But when I'm looking at Z here, I don't think your silvers, I'm gonna have a silver left over. Do you see what I'm saying? Like when you try to combine them, your silvers don't completely cancel. Unless you multiply by something. What do you have to end up multiplying by? Gee, let's see.
Let's just,
But do you see what I'm saying about the 2 silvers and the 3 silvers?
This is 3.
flip of it.
There's no
Okay,
silver.
no, one of them needs to be multiplied. X
Right.
needs to be multiplied by 3, and then Y needs to be multiplied by 2. It says it.
Right. Down there. Okay. Yeah, so if we multiply this one by 2 and that one by 3, they combine to give you that one. So this ends up being, because the silvers didn't cancel unless you multiply. But if you do multiply by 2 and 3, it that doesn't change the voltage. But a light should have went on your head and said, that's not going to quite cancel out. So anyway, 1.54 minus 0.94 gives you 0.60. This comes up sometimes, y'all. And so, like I said, it's kind of a system. That's what's called in math, a system of equations, where you have to combine them. This is a thing. So, yeah. This one was tough. This one was tough, but I think you got it now. Hopefully that kind of jars your memory a little bit. What I was trying to do in my head, and it didn't work out initially, so I kind of had to abandon that. I wanted one to stay constant and be able to solve for the other one. That wasn't, so in this situation, you have to kind of combine them and get that third reaction. So, kind of tricky. Here is another question. Maybe you'll find this one to be a little bit better for you. I think it will. I think you got this. In galvanic cells X and Y, which of the following takes place in half cell 1? Notice half cell 1 is given to you here as you go to answer it. Okay, here's half cell 1. So it's this first reaction, which can be done as written, or it could be reversed and be oxidation of 10 instead of the reduction of 10. That help? Got it? Yep. All right, so this is reduction. Like I said, these, if they gave you the voltage here, these are always given to you as standard reduction potentials, like I said. So the cell potential there will always be reduction. Now, if it gets reversed, then that will be oxidation. So you can see here that this actually gets reversed, and so this is oxidation, and this actually goes as written times 3, but it doesn't matter. All right, there's 3 of them. It doesn't matter. And this is reduction. So it looks like the right answer is C. Right. So that one, that first question you struggled with, that's fine, no worries. The second question, a lot of times when you have a series of questions, the second question could be easier for you. So don't give up on a whole problem because you can't do one part. So here is a real FRQ based on cell potentials and galvanic cells. Yay! So this is 2 parts. So I'm going to say you're circling and you're writing a net ionic equation. I'm going to give you about 3 minutes. So take about 3 minutes for this.
Just put the answers up.
Oh no! Don't look. Avert your eyes. Thank you. Take about 3 minutes for this. No! I'm trying to write. I'm sorry.
Oh, I saw the answer.
You saw the answer? Oh, I'm sorry.
I don't think you went back to the steps.
Thank you. I was about to do it again. Take about 3 minutes and erase your memories and do this question. Need a hint? Uh-huh. Okay, so do you get that the student wants this reaction to take place? Yep. Okay, so recall that the solution, or excuse me, the path reaction with the highest reduction potential will be the one that gets reduced. So, if he has access to sodium that's not thiosulfate, that is, maybe that is something. Anyway, so he has access, that's that, yeah? You see that spectator? And then he has this. So that sucker's gonna have to go backwards. Right? I'm sorry, the other one, oh, I left one off, didn't I? Wait a minute.
That one happens if you reverse the first time reaction, right? Like you get the.
Yes,
Yes.
you're right, good job. Yeah, this one is if you go forward. This one is if you go in reverse. Yeah. So, you want this to be your highest reduction potential, okay? So whatever it combines with needs to have a lower reduction potential than that. Do you get it? No. Huh?
My brain's no longer working.
When we have the two half reactions, remember whichever one has the highest reduction potential will be the one that gets reduced, and the other one will be the one that gets oxidized. So
And we can't have a negative voltage, right?
can't have a negative voltage.
So,
What?
like the total can't be negative.
Well, if the voltage is negative overall, it won't happen without outside intervention
Okay, yeah.
because
That's what I-
it will
that's what I was
have
thinking.
positive gives free energy. Is that? This one's y'all look so defeated.
Wait, no, go back to the thing.
Are my lines
The
confusing
highest
you?
What value is gonna get?
So when you're looking at reduction potentials,
Yeah.
which half reaction has the highest reduction potential will be the one that actually gets reduced. Okay. So you have three options here.
Wait, isn't there a chart for that too? Like.
They gave it to you,
You only need those 30.
so you have it.
Okay.
But what if you make the 0.68, what if that's negative? Does that count? So like 40.4 will go before it because it's
Yeah,
negative?
0.54 is definitely larger than 0.68, negative 0.68.
That's okay.
Yes.
That's what I was asking. I wasn't sure if the negative was taken into account.
Would it help you if we wrote the voltages here? Like maybe the drawing the chart, did that confuse you?
No.
I'm just confused because I thought we already knew that I don't know when to be reduced.
It does want to be reduced, but I'm saying you have to figure out which one it can react with. For it to be reduced, something's got to get oxidized,
Yeah,
right?
I bet it's the second one.
You think it's the second one?
I just don't know how to figure out which one.
That was.
In A2, right?
You thought it was the third one.
It's like you gotta put the top one.
So, okay, life lessons. If you're having trouble with E, what should you go ahead and do to get your points? Yeah. Ooh, yeah. But you know what? If you pick the wrong one, I think you'll be penalized in E, but as long as you write it correctly, I think you would get the point in F. We can look at the key in a minute. That.
You know, I remember we had trouble with this like during.
Yeah, this is not easy. This is not easy, and we did it pretty quickly at the end of the semester.
But not this
Go ahead and pick one and write your balanced ionic equation.
one. Yeah, see, I don't know how to do that. I'm not gonna do this. I'm gonna do.
Give it a try. Your AP exam's in a week and 2 days. I love you so much. Just plow through it and we will talk about it. Have something to start with. I have made my choice.
Oh no, it's a.
This one's tough. It's okay. It's okay. Do you get that on F? You're gonna have to combine your half reactions? Yeah. Okay. That's good. Yes.
I just don't like how the first one is still too negative after you have the electrons added.
Yeah, that confused me. I don't know how it helps. Like,
Are you talking about right here?
No,
no, the first reaction, the first half reaction. Like, I don't know.
it's too negative, then you add two electrons.
Oh, okay.
Because it turns into.
If you
the-
break down the if this is bothering you, what you do is if you do the oxidation numbers, do you want me to write out the oxidation numbers for this and show you what happens? Probably the sulfur's oxidation number changes if I'm guessing, but I'm pretty sure that's what ends up happening. I can show you that, that's not a problem. So if we, so if I break this down and do the oxidation numbers, I have 6 oxygens, and they're 2 minus each, and then I have an extra 2 minus. So that is, 14 minus? Okay. So, the sulfur, doesn't come out.
Isn't it supposed to be 12?
Yeah, it would be 12. It's
Yeah.
12 plus.
Oh, right, because I have
2 electrons.
2 more electrons. 2 minus is 2 more electrons. That would be 14. That's very interesting.
So that means the S's are worth 3 plus each. Right?
Well, there's 4 of them.
Yeah.
Well, this is going to be, each one of these is 4 plus. The oxidation number of sulfur changes. But as far as how that doesn't work out, oxygen's oxidation number generally is 2 minus in this situation. It may be something different. Perhaps it's 1 minus, I don't really know. Sulfur's not one that you can bank on either.
Why can't that work? If you,
There's 4 sulfurs and 14 electrons. 14 divided by 4 is not an even number.
I don't know how to
Well,
do
why would it be 14?
Well, it's not
Shouldn't it be
canceling
12?
out.
Because it's 2 minus.
There are
Yeah.
You're not getting rid of
6 oxygens, 2 minus each. Then there's 2 extra electrons. Oh, I see what you're saying.
So it should be
You're
12.
adding 12.
It should be 12 in total,
Well, how
and
do
each
you
is
do-
worth 3.
How do you do
Yeah.
the other side, like the ones, but how do you do the coefficient?
You have 2 extra. I see what you're saying.
Yeah.
Oh, yeah, you're right. I
Is
got
that
you.
right?
So
Or
each one is 3 plus.
each one is 3 plus.
Yeah, you're right. So So the sulfur goes from 3 plus to 4 plus. Thank
What?
God.
No,
No,
it's
wait.
not 4 plus here either. It'd be 3
It's
plus
3
there.
plus.
So it's the
Ooh,
same.
so it doesn't change.
That's where I was confused.
How was that 3 plus right there?
Because it's negative.
Let me
14
draw it out
total.
for you. Let me draw it out for you. Look,
Oh,
there's 1
dude.
sulfur.
Okay.
There's 2 sulfurs, there's 3 sulfurs, that's 12 plus signs, and then 6 times 2, yeah, that's fine.
And that's what's going on.
So Tate, you're stuck on the fact that this doesn't work for you? It's not funny, I'm sorry.
I don't
That
like
still
how it looks
doesn't
like
work,
nothing
right?
changes charges.
Yeah, that's
Because the
it
sulfur
confuses
stays
me
the
so
same
much.
charge, so the oxygen.
They were really.
I don't think, I mean, I feel you, I see what you're saying, because it doesn't look like the sulfur's, oxidation number changes,
Now, how do you do the other side?
but that doesn't really matter for this problem.
Wait,
That doesn't matter.
aren't we, so because we need the iodine to be reduced.
Yes.
We're looking for something that oxidizes, right?
So
So
what?
it's not the top one involved.
Well, you gotta remember that the one that has the highest reduction potential is gonna be the one that's reduced, and it's gonna go as written. The other one is gonna be the oxidation half reaction. You're gonna flip it.
Okay.
I think we need to just let me show you. Yes, ma'am.
How do you define like, the numbers for 2S2O3?
What do you mean?
Like
How do you find the oxidation numbers?
Yeah.
I tried to like be all quick about it. You know how I always showed you to like actually write it out with the plus? Let me just do that. Let me take that over here. So there's my oxygens, right? This is it. Look, I have 2 extra minus signs. The charge on each one of these is 2 plus. So the oxidation number of sulfur goes from 3 plus to 2 plus. Do you see how I tried to take a quick shortcut and I screwed it up? Do what I showed you how to do.
Okay, but what do we do with the coefficient? How does that
It
matter?
just means
The coefficient, there's just 2 of them. That doesn't change the oxidation over sulfur.
Okay.
There's 2 of these. That's all.
Wait, it's 2 plus? I thought it was 3 plus.
Wait, over here it was 3 plus.
And then on the other side it's 3 plus 2, right?
I just worked it out. It's 2 plus. See?
But you only have 6 of them. You don't have all 8.
What are you talking about?
there's only 3 oxygens.
There's 3 oxygens, but then there's 2 extra minus
Oh,
signs.
no, it doesn't change it, does it?
Yeah.
Darn it.
So it is 3 plus.
I don't know. Look, but I feel you, Tate. I will ask somebody smarter than me what happens in this first half reaction because I don't know. But that isn't important for this equation. Like to write this out, you don't need to know that. But I'm glad that you noticed that. I mean, that's boggling my mind too. I don't know. It doesn't appear that the sulfur or the oxygen's oxidation number changes. So
So they have to be oxidized?
yes, it's a redox reaction.
No, let's solve it.
Are you still working on it?
Yours was right at first.
What are you talking about? The oxidation numbers. Listen.
Before you added those extra pairs.
So that wasn't right because she only had 6 minus signs in total, but there should have been 8.
Yeah, because you had 2 extra electrons because the charge is 2
Yeah,
minus.
because it starts 2 minus.
I was feeling good about myself. I was trying to make it work, but it
It
doesn't.
still would have worked out though, because you only had. You had.
You would have to have 8 and 2 extras.
What about 8 and 10? No, that
It doesn't work, man.
Oh.
I think y'all are missing the forest for the trees because this is not even a tree that we need to worry about.
Oh, really?
What we were doing with the oxidation numbers right now, you need to pick the right half reaction, and then like I think
Wait, we need
No, I
to
still
do that though
can't
to
move
figure
on
out.
from the like.
Are we gonna figure it out?
Yeah, we need to do that though to figure out which one oxidizes, right? We need to do that for the first one.
Well, no, you already had the reaction. You don't.
this is all these half reactions are reduction half reactions.
Okay,
They
can
are
we
reduction half
finish
reactions,
and
and
then
these are
come
reduction
back?
potentials. I worked it out. I don't know what get the oxid. It's very possible. Listen, it's very possible that the oxidation number of oxygen may not be 2 in this situation, maybe 1. That's not. It's not always that, but it generally is. You see what I'm saying? That's probably what it is.
I just knew it was the middle one.
What?
I knew it was the middle one.
This is what we
I would
get
think
the
that
closer
you would-
reaction.
Yeah.
We want it that
Because
way.
you have 3 oxygens.
Yeah.
So you have
That's
2
why I was
I'll
it was
probably
the middle one.
And so
I-
2 electrons. So the S2.
But I'm just confused about that whole thing.
No,
about two
there's
powers.
3 pairs of 2
I don't
electrons
even
in
know how to
total
write the
because
equation.
oxygen is 2 minus.
Okay.
Yeah.
I think we just need to go and work on this. Let's just go over it. We've had some good.
You added 2 more.
Oh, that's
You were
right. That's
first.
right. You were right.
Canceled them.
You were right
And
because
it-
there needs to be 2 left over.
Yeah, and 2
Yeah,
are
but
left over.
they
That
do it
third
on the left
oxygen
side,
is
you
left
can't get
over.
the math right.
You know when you had 2, 4, 6?
Oh, yeah, but then if you do it on the left side, you can't get the math right.
It was
Let me
getting
get that.
intense.
I'm doubting my life.
Hold up, wait, can you
Y'all have confused
draw-
me.
Can you draw what you had again?
Okay.
You had the 2, 4, 6, you had 3 oxygen.
What if there's some like
I think the oxygen-
I'm not, I can't move on to that until.
I love y'all. Okay, I think I was right, and
Yeah,
Jonathan
you were.
screwed
because
me
they
up.
canceled.
Okay, Lord help. To get this is not even important right now, but to get
I'm really bad at this. Like, I
Yeah.
can't think straight on this.
Yeah, and then you had you have 2 left over. Yeah, that's
The
what I was saying.
oxidation number of sulfur goes from 3+ to 2+, and we're done.
But it's not 3 plus on the other one, you did it wrong on the other.
Yeah,
Oh my
yeah.
God.
So now we gotta
Okay, let's go over here and do this one. How to assign oxidation numbers when it's not necessary right now.
No, that won't work though, will it?
What?
Hold up.
Hush your face. What are you talking about?
No, it's
There's 6 oxygens. 1, 2, 3, 4, 5, 6. Okay.
7, 10.
You need 10.
Oh.
Ah! Oxygen's number is the one that changes, right?
Wait, but that works.
Not
Because
sulfur.
it'll be like 2 point something, won't it? So it's
No, that's not possible. That's not possible.
There's
There's something going. Listen, I love y'all. I'm so glad that you're so curious about the oxidation numbers of sulfur and oxygen, but that is not necessary right now. Okay, it's just not. You
So
already.
that's how you do it,
You're
though, right?
already get. Yes, that's how you do it. You're already given the number of electrons transferred. Just it's okay. That's not the purpose. I promise on my life I will find out what is going on with that reaction for you, but not right now. God bless y'all. I'm not sure. Are you ready to look at this one?
Uh-huh.
Okay, that's great. So what they ended up saying was the middle one, which is the one I was feeling that was right. But listen, the reaction between S2O3 and I2 will be thermodynamically favorable because the electrical cell potential is positive. From that, the Gibbs free energy is negative. So if we go back and look at it, what? Let's do it and go back and show you. So it's this one, okay? Oops. It won't. There we go. I can't get it to show up my pen. But it's this first reaction here. There we go. And so you're gonna have this one will be the oxidation one, right? And so it will be negative 0.08. So I'm making me tired.
But the justification is just that it's
Like for example, if you had chosen the hydrogen peroxide, it's gonna this has to go down like it's written. This has to be your reduction.
Yeah.
That's what you want to do. So one of these other two has to go reverse. If you picked this one, right? That's in that, right? If you pick this going forward, that's a reduction reaction. You can't do that one. This one can't be it because, do you see what I'm saying? That's what was tripping you out. I didn't want to just say here's how to do it, but that's it. If you pick this one, that's a reduction reaction. You can't have two together. It's a redox reaction. You have to have, one of them has to accept electrons. So either this one or this one has to go that way. If you pick this one going that way, it's going to be, the cell potential will be negative 0.08. If you pick this one going that way, negative 0.68, and that will give you a negative cell potential, and the Gibbs free energy will be positive, will be thermodynamically favorable. Make sense now?
Yeah.
I'm sorry, y'all look so sad. These are hard, but that's good. I'd rather you be sad right now than in 9 days.
So
So how do you write the
Okay, so the reduction one goes as written, and because they all have 2 electrons, you don't have to do anything to balance out the number of electrons. So all you do is just write this one as written, and this one gets reversed because it's the oxidation one. Look at me in the face. The way you build a cell is that and this isn't a cell question, but the way you make a redox reaction is the one with the highest reduction potential will be the one that's reduced, and the other one by default has to be the oxidation one, and it's going to have to go backwards. You're going to flip the sign on the cell potential. Is that ringing a bell now?
Yeah.
It's been a hot minute. I know. I'm so
So I was
sorry.
never
Sweet
good
children. I know. It's okay. Whee! Okay, so when you look at the reaction and you combine them, this one is what was written, and there was 2 electrons in there, and the electrons cancel out. It was this plus 2 electrons give you that, yeah? And then the other one had the electrons on that side, and they cancel. You just combine them. That's it. Now, if one of them only had like one electron, for example, you would need to multiply that whole equation by 2 to get 2 electrons. But the electrons did cancel. That wasn't necessary. Silence falls over the crowd. Are you still stuck on the oxidation numbers?
No,
Or still like,
shouldn't that change
what? This one?
on the right side?
This?
Not the, yeah.
That? All right, let's go back and look at it. Okay.
Shouldn't charge change or something since
Mm-mm.
it's
Start like
This one goes in there, and this one is going this way. Yeah. This is the oxidation. So it goes from there to there. Y'all, I promise on my life I will find out what's going on with that first reaction. I promise y'all. I appreciate your I promise. Notice the coefficients from the original reactions are still there, right? No problem there. I think we need to do some redox practice. Yeah, it's okay. Whatever. To determine the molar mass of an unknown metal M, do y'all need like a little break? Y'all's brains look super fried. You look super fried. Let's just take 3 or 4 minutes, and I will just mute this.
Right, but I'm not,
I'm gonna go
Counts.
see that.
you're gonna go eat it.
I'm gonna go see that. No, I-
You're gonna go eat.
Cause I know it's not gonna be, if I start losing it after a while.
yeah, that reaction happened.
And that's just made me mad.
It's okay. No worries. I'm glad y'all asked. I don't know. I see what you're saying now after looking at it. right, sweet children. I think we all need to do some redox practice. That will happen for you. I'll give you some things. Here is the first part of an FRQ, and you can see here what's happened. To determine the molar mass of an unknown metal M, which is what they generally do for an unknown metal, a student reacts iodine with the excess of the metal to form the water-soluble compound Mi2, as represented by the equation above. The equation is cut off. It'll be okay. I'll get that for you if I need to. The reaction proceeds until all of the I2 is consumed. It's probably just M plus I2 gives you Mi2. That's probably the reaction. I think you're good. The Mi2 aqueous solution is quantitatively collected and heated to remove all the water, and the product is dried and weighed to constant mass. And notice that's that repeated drying and massing. The experimental steps are represented below, followed by a data table. So they massed the metal, they added the iron and iodine, there you go, and they added the water, the reaction. They gave you a nice little picture. And here's a bunch of data. In your mind already, you should be going and thinking, okay, I need to go to moles. And notice on B, I've told you a couple times today, you're asked for molar mass. What do you need to do? You need to think about what molar mass means. If I asked you for the molar mass of sodium, you would tell me it's 22.99 grams per mole. So you get on there, they ask you for molar mass, think about grams, think about the number of moles, you need to divide them. So I'm going to give you 3 or 4 minutes to try this one out and see how you do. In this data table, you should be able to find the grams for iodine pretty quickly. This one's a little bit tricky, so keep with it. I believe this is from last year's FRQs. This is a real exam question from last year. You guys got it? If you have trouble with the molar mass, you can think possibly back to Bouts equation that may help you. guys got it? No? Have you at least found the number of moles of I2? Yeah, okay. Do you need more time? Yeah, okay. I think some people just figured that second one out. Or maybe your face looks like it is. Maybe your face looks like you figured it out. Did you find it with zinc? Yay, zinc. Okay. So let's talk about this. There's a few things here that you need to be aware of. First of all, if you read the question, it says that you have excess of the metal. Okay. So the mass of this metal, if you take it from this step, that's not going to be correct as far as using it for part B. You're going to need to use the data down here and the data from the iodine and all that. Okay, so let's look at it. Given that the metal is in excess, calculate the number of moles. This is real straightforward. You know, you just subtract. They were very generous with what they gave, and then you found 0.004023. Notice here, you have 4 sig figs, and so your answer has 4 sig figs. These are not significant. If you can leave them out when you do scientific notation, those kind of just placeholder zeros. Now, this number, if you think about it, the final, formula for this was, Mi2. Well, you know the mass of iodine, just right there. So the mass that was recovered, it said this in the chart, right? That was after the second massing or whatever. This minus that iodine tells you what's left of the metal. You can't start with that first metal measurement because it was excess. So again, if you're asked for molar mass, you need to just think, okay, molar mass is grams per mole. So there's your grams of the metal, and the moles of the metal are the same as the moles of the eye,
Oh,
I
that's so
too.
close.
right? And so 65.4 grams per mole. And you know what I did when I finished is I looked up at the periodic table. When they made this, people that make the AP exam, they're probably going to find a molar mass that's actually a real one. And when I saw that I had gotten zinc, I was like, all right then. So you can kind of check yourself on that. So there you go. That one should have been okay. Should you feel better about that one than the redox? Good. Okay. All right, so that is Big Idea 3. What I'm going to do is I'm going to stop the video, and the reason I'm going to do that so I can start a new one for Big Idea 4. So if you're listening in, I'm going to start it right back up after I stop it, just so I have separate videos. So kinetics, this Big Idea is really, it goes pretty quickly. As far as the amount of content, it's not that bad. When we talk about kinetics, we're talking about rates of formation of products, rates of consuming the reactants, rates. If you remember, when we are making new products, they have to not only collide with enough energy to form the activated complex. The activated complex is this temporary, unstable kind of arrangement before so the bonds are formed for the products. So they have to orient themselves properly, and they also have to collide with enough energy. So that's collision theory. The rate increases as state changes from a solid to gas. Gases are going to have increased molecular motion, so you're going to have more collisions more often. Okay, greater surface area. They ask a lot of questions about this, and they're really simple. Like if you take a metal and you crush it up, or if you take a solid and you crush it up, or anything like that is going to increase the surface area. So those are easy questions. Don't miss them. More kinetic energy, because the temperature is higher, is going to lead to more successful collisions. And the concentration, the more reactants you have, the more collisions. And then if you use a catalyst, it's actually going to give you an alternative reaction pathway that has a lower activation energy, which I mean that the energy needed to make an activated complex, it might even be a different activated complex. It's a different reaction pathway. It's a different route to get to your products. So that the catalyst can speed things up. Yay, FRQs. A student designs an experiment. I think we already did, if you recall, we already did A, right? But we have not done B and C yet, have we? Nope. We only did A. And that was where you had to say it was acid-base because a proton was donated from the acetic acid to the bicarbonate ion. Okay, so a student designs an experiment between sodium bicarbonate and acetic acid, and there is the mass for your sodium bicarbonate, and they add. When you see this milliliters and you see this molarity and you're about to have to do a reaction, what do you need to change it to? Moles. That's exactly right. And notice, as soon as you see the words, find the limit to reactant, guess what you're about to make? A BCA table. So go ahead and make yourself a BCA table for Part B. They don't make a BCA table on the AP exam key, but a lot of people that grade it, they make those and they know what it is, so you can feel very comfortable doing that. And then Part C is actually the kinetics part. The student observes that the bubbling is rapid at the beginning and gradually slows as the reaction continues. Explain this change in the reaction rate in terms of the collisions between the reactant particles. So B has a little math to it. Good for you. It's good practice. And then C is kinetics. Hey, you should be finishing up part C. We already did A earlier. Alright, so you guys got it? So I can tell that, if I look at the balance equation, that I have 1 mole of sodium bicarbonate reacting with every 1 mole of acetic acid. When I solve for moles, I have 0.0525 moles of acetic acid, and I only have 0.0273. If the mole ratio is 1 to 1, or if we think about this with a BCA table, and I start here with 0.0273 moles, and this one I start with 0.0525 moles minus x for my BCA table, right? Which one is going to have the smallest x? Which one's going to run out first? The sodium bicarbonate. So you should have found that to be your limiting reactant. And notice that says justify your answer with calculations, which we did. On the second one, or part C I should say, oops, let me make that go away. Whoops. Oh, they didn't make you do part C, but part B, but it was good for you. I'm glad we did part B. I mean, you would have had to do it on the AP exam, and it's good to practice. But on part C, that's actually the kinetics part. As the reaction proceeds, the reactants are consumed, so their concentrations decrease. So as the reaction goes through, the concentrations will decrease, and so that will reduce the number of collisions. They'll be less likely to occur, right? And so the reaction rate slows. That one's pretty straightforward. I'm glad we did the limiting reactant problem. All right, rate order. Okay, so rate law for reaction, if you recall, this is not on the formula sheet. It's not. So you have to remember that the rate of a reaction is equal to the rate constant times the concentration of reactant A raised to a power. This is not good. This is not equilibrium. These exponents are not the coefficients in a balance equation. These have to be determined experimentally, right? So experimentally, you can determine if this is the reactant A is 0 order, 1st order, 2nd order. Ringing a bell? Oh, okay. Only the reactants are part of the rate law. The exponents are determined experimentally. This is not kinetics. In kinetics, you have an equilibrium. This is not equilibrium. In equilibrium, you have equilibrium expressions and blah, blah, blah. And so that is the situation where the coefficients are, exponents. Kinetics, this is not it. And this is not on the formula sheet. Oops. We'll get to that in a minute. That looks fun. So just want to remind you about that. So what will be given to you is you will have data that is determined experimentally. So when you're given data and you have to determine the rate law, what you're going to do is you're going to hold one of them constant and see what happens. So you can see from trial 1 to 2, the concentration of B is held constant, A is doubled, and we see the rate law, and the initial rate, doesn't change. So what you have to do, this is a free response, you have to say when the initial concentration of B is held constant and A is doubled. You have to, when you hold them on constant and you're making comparisons of the initial rate, of the initial rate to the initial concentration, you have to say that you hold the other one constant or you get no points. So as the initial concentration of B is held constant and A is doubled, the initial rate stays the same. So this reaction, the for the order of the reaction in regards to A, it's zero order. So if we look at this rate law down here that they provided to us, we can see that it has, it doesn't have A in it. There it goes. So A is left out because it's zero order. What's anything to the zero power, y'all? 1. So that's why it's not in there, okay? Then when we go to find the order in regards to B, we can see from trials 2 to 3. So say the trials are comparing. In trials 2 to 3, the initial concentration of A is held constant, and when B is doubled, the initial rate doubles. So when it's 1-to-1 ratio like that, B is going to be first order. So the rate law is rate is equal to K equals B. To find the actual value of this constant, you're just going to put this number here and this number here and solve. You pick any trial. It does not matter which one. Do y'all remember how to do that? Yeah. I tell you what. Why don't y'all go ahead? It's not a problem. I don't care. It doesn't matter that it's not here. I want y'all to go ahead and find me the rate constant for this. Find the rate constant for this rate law. This is definitely something they'll ask you to do. Does not matter which trial you pick. So just looking at this without a calculator, right? I'm gonna take it, I can take the first one, okay? If this is 0.002 is equal to something times 0.1, what did you get? 0.000 point something, how many zeros in a 5? 0.0 what?
0.02.
Oh, right, because I'm not dividing. So 0.02. So no matter which ones you figure to pick, it doesn't matter. You'll get the constant will be 0.02. So I'm afraid when you get in there, you'll be like, oh, how do I find the rate constant? The data's right there. Just pick any trial and you fill it back into the rate law. Okay, you have to find the rate law first. You guys are good at this because I have a little trick for you. So a zero order, if you plot concentration versus time, it will make a straight line, okay? And the way do you remember how I told you to remember that? Do you remember M&M is like a circle? For zero order, see that's a circle. For zero order, molarity, which is concentration versus time, is a straight line. If it is just concentration, which is molarity, versus time, and it's a straight line, decreasing, then it's zero order. Ringing a bell? Okay. And then I told you on this one, the natural log of the concentration, an L kind of looks like a 1. So the natural log of the concentration versus time, if that's a straight line decreasing, then it's first order for that reactant. And see, notice this is single reactants. This is A. So this doesn't give you the overall rate law for all of it, but it gives you the rate law in regards to that one reactant. So second order, you can tell the slope actually goes up, and then think about it, you have to write 2 things down. So second order, 1 over the concentration of a reactant, that will tell you that this is second order in regards to A. Now look, why does this one go up but these go down? Over time, as the reaction proceeds, this number is going to get smaller. So 1 divided by 1 is 1. 1 divided by 0.5 is 2. 1 divided by 0.25 is 4. So as this gets smaller, that is going to increase, and that's why that slope is going to be positive while those other 2 are negative. Okay, good times. Math is fun. So the first and second order integrated rate laws can be found on the formula sheet. So these actually are on there. So if you look, the kinetics part of the formula sheet is pretty bare. It's on the bottom of the first side. You guys see it? you're given the rate law you're given, excuse me, the integrated rate law, for first order and second order. You guys found, and that's it, that's all you're given. And then, so the one, oh, actually, I'm lying. You're also given the half-life. You have given the half-life, and so that half-life formula is for first order reactions, that's actually. Okay, so you may need to take values and plug them into those formulas on the sheet. How you guys doing?
Tired.
Getting tired. I'm sorry. But I'm not really sorry, right? I don't mean it. At high temperatures, the compound C4H6 reacts according to the equation above. The rate of the reaction was studied at 625 degrees Kelvin in a rigid reaction vessels. 2 different trials, each with different starting concentrations, were carried out. The data was plotted in 3 ways shown below. There's that. And I guess there are some questions. Yeah. So you don't really need that beginning part so much right now. So use the data plotted in the graphs to determine the order of the reaction with respect to CH4. The initial rate of the reaction in trial 1 is 0.0010 moles per liter. Calculate the rate constant K for the reaction at 625 degrees Kelvin. So
Can you rewrite that reaction so it's simple?
the reaction is just C4H6 breaks down into, or
Two of them does.
makes, I think that's a CH814. But if you remember, if we're doing kinetics, or are you particularly worried about products? Doesn't matter. So this is your reactant that we're worried about right now. And there's only one reactant. So we can't really zoom in on this right now, though, because it's in the PowerPoint mode. I can't switch it. So you're looking for a straight line. Yeah? You see a straight line?
Yes.
Yeah.
You go then. Here's your question. On this question B, is it asking you to justify? Is it asking you to explain? No. So have you all successfully determined the order? What is it?
2.
Second. So guess what? You're given some data, and then are you you're gonna use this graph, right? And if you use this graph and you use the formula for the second order integrated rate law on your formula sheet, you should be able to knock some stuff out. That's what you're gonna have to do, okay? I wish you well. I'll give you a couple minutes to look at that. You may need to come a little bit closer so you can see some of the data.
What is T in the formula?
T is time, and then there's like a not symbol in the formula, yeah? Okay, so good question. So if you look at this kinetics formula, the 1 over the concentration at AT, that's your final time that you're going with. Now you can pick, this is a straight line, right? It doesn't matter what point you pick. Pick a time, doesn't matter. So it doesn't have to be the final time, it could be any time. Minus 1 over the initial concentration, that 0, that not sign there, that's the initial concentration of A equals KT. That T that you pick, like for example, if you go with 20 seconds, then you have to equal it to K times 20. You got a negative number?
Yeah.
The formula itself, for second order, doesn't have a negative sign, does it? It's only the first order that's a negative sign.
Oh,
This is like this is your initial concentration, and that's the final time. The initial concentration has to be at 0 seconds, my people.
Yeah.
We're doing trial one? Oh, that's the problem.
If you pick trial 2, they're both straight lines, right? So it shouldn't matter, but you better stick with the right line. Whatever line you choose, stick with. You're solving for the rate constant. Math is fun.
Wait, so you can't get a negative number?
For the rate constant, did y'all both get negative ones? I don't think that's, I don't know that that's, you can't have a negative concentration. I think that's what y'all are thinking of.
Okay.
Yeah.
Have a negative rate.
Huh?
You have a negative rate.
Well, if you think about it, if you're thinking about the rate at which the reactants are being used, they're going to go down, right? So when you graph it, you're going to have a negative slope. So as far as the rate, like the initial rate, so those will not be negative. Like when you're looking at that chart, if that's what you're thinking of, they'll be positive.
That's the initial concentration, just the violence, right? And then this is whatever one that is more.
Have y'all all found a K?
Yeah.
Yeah, okay. So it's second order because a plot of, and notice this is in parentheses because they didn't tell you to justify, right? So you just had to get the right order. Don't get too much when they're not asking for it. You're going to save your time for when you need it. So here's their rates. For the second order rate law, they filled in, here. This is probably what y'all used.
I don't know what that is.
What?
What's our
That's a great question.
What's the answer?
It says 2.5 liters per mole second.
Oh, 0.66 negative.
So we didn't use that.
When you look at those lines, like K is equal to the slope of the line. So it looks like they just went with slope.
Oh.
Yeah. Do y'all recall that? I would have probably done the formula too, and you should have gotten the right answer. But I wonder if this 2 that you really couldn't see, I think that might have been ended up being a 4. I was like, you're fine. I'm sorry. But K was equal to the slope, so that's just that's what they did. Now, as far as the 2 there, students who choose the second method to determine K but omit the factor of 2, thereby getting an answer of 5, still earn the point. But y'all said y'all got something negative?
Yeah, because I just plugged stuff into this equation.
Mm-hmm.
And it didn't work.
So we can't, because that thing is using the coefficient.
Wait, can you go back to the graph real quick?
Sure.
See, it's already 1 over choices. Instead of plugging them in. You wouldn't plug them in. That's why.
Because it's already given to us. Okay, I gotcha.
That's because I got that.
So you already can tell the rate law. Rate is equal to K because you already know it's second order. Mm-hmm. Not fun. Gotcha. In any of these cases, though, when it forms a straight line, k is equal to the slope of that line. So that's what they went with here. And they said they still gave you the point there if that's what you chose to do.
I got 5.
Wait, so.
And if you got 5,
Can
you
I
got
try
the
to
point.
look it up now?
Why 32?
So since you know the order, yeah, that's my fault for telling you that.
So,
I was like, in the formulas on the form sheet. Just kidding, you don't need it.
so if you got 5, they give you credit.
Did you get 5?
Yeah, after I did it the right way.
Okay.
So what is that formula used for
The
then?
formula is used for, like, if you know something is second order and you know the concentration initially, but you don't know it after a certain period of time, but you know the amount of time, you can fill it in.
Okay.
Yeah, but that was, like, we took it way too far because you were given everything. So
Okay,
you
I
actually, the easier thing to do is just to fill it in the rate law because you already know the rate law. So, yeah, the formula that we use would be better, like, if we needed to find the concentration after a certain period of time. So, but this is what you guys ended up doing. Some of y'all did this, though, right?
No.
No.
Well,
Yeah, now we're taking
yes,
the values
but there
and
was
putting
no
them-
2.
Yeah, I need to check about that because I didn't. That's a little bit hazy for me. Okay, so I think the fastest way to do this would have been to use the idea about k equaling slope, right? That would probably been the fastest way. If you already have the line, sometimes you're given data and you don't have a line, and then the formula you use would be better. Okay, so the other formula on your formula sheet is for half-life. And so they show here how they figured that out and how they derived it and everything. For a first order equation, this half-life equation on here, this T half is equal to 0.693 divided by K. That only works for first order reactions. That doesn't say that on your sheet, so you need to know that. Time needed for the concentration of reactant to reach half its initial value. The time to reach half the concentration is dependent on K, not the initial concentration. So, half-life remains constant for first order reaction. So, when the half-life is 30 seconds, the concentration is half every 30 seconds. And so, if you knew that this was 30 seconds, you could actually fill that back into the half-life formula and find K. So, if you knew the half-life was 30 seconds, you could put that over here. So the natural log of 2 divided by K would, the natural log of 2 is 0.693. That's the number on the formula sheet, okay? So anyway, you can fill that back in. That's pretty straightforward, but that's only good for first order, okay? Because that's the only one that has constant half-life. They will ask questions that require you to have that piece of information that the half-life is constant for first order, but not other ones. So if you're looking at a data table and the half-life is staying constant, then you know that it's a first order reaction. They've done that before. Collision theory and reaction mechanisms. In a successful collision, molecules have enough energy to overcome the activation energy, and remember they have to collide with the correct orientation. We already talked about that. And a mechanism, so this is the reaction mechanism. It shows the elementary steps, the individual steps, okay? The rate law of any elementary step or reaction can be written from its stoichiometry. So this is where people get confused. So the slow step, the slow elementary step, in this case, the rate determinant step, is going to be this first one. So in this situation, you can write the rate law for this based on the stoichiometry of the slow step. So my rate law for this reaction is based on the reactants of the slow step. If this had a 2 right here, y'all, then that would be a 2 right there. That's the only time that the coefficients in a reaction can be used to write a rate law from the elementary step that has the slow or the rate determining one. How do you feel about that? Do you remember that? Mm-hmm. Okay, so if, for example, if, well, you know, if step 2 had been the slow step, you can look at that and you can see that these, well, that goes back and you still have the same rate law, but so that's not going to help you. I'll try and give you another example. All right, because these are those reaction intermediates. Remember, if the rate determinant step has those intermediates in it, you have to kind of follow them back. Ringing a bell? Yeah, okay. Oh, oops, we already did it. The rate determinant step is 1. So, okay, so here is the Maxwell-Boltzmann distribution. Do you remember him or them? Those. Assume that all these curves show the distribution of molecular speeds in the same substance. And so if you recall, this is the speed. And so A looks like, you got to be careful because A looks like it has the stuff that the speed is the highest, but that's not actually right. This is the portion of them that are going at this slower speed. And so as we heat something up and it gets more kinetic energy, you actually see that the higher percentage of the molecules will be going at higher speed. So D is actually, I'm not going to answer the question. Question, which curve indicates a particle is most likely to produce collisions that result in chemical change? Justify your selection. So just go ahead. Did I accidentally go ahead and, I'm sorry. So it's D. This was something that y'all are always really good at. So curve D, because a larger number of particles have higher kinetic energies, and so they're more likely to overcome the activation energy. Okay, so these are two reaction coordinates or pathways. So in order for reaction A and reaction B to proceed in the forward direction at the same rate, which reaction would need to be at a higher temperature? So this one is a good application of what we just talked about. So go ahead and write down your answer. See, there's a little button in there. Go ahead and write that down. Think about it. Y'all seem to not be having any trouble with this. Okay, so y'all are all saying A, and the reason you're saying A is why? Has a higher activation energy. So the higher activation energy, the slower the reaction. Since A has a greater activation energy, it should be slower than reaction B. So if you think about it, if we could somehow smush these together, and it's not gonna look like this, but I'm gonna draw it in. Let me do that for you. Like if I could somehow smush these together and make one line, this would be my first elementary step, and this would be my second elementary step. I mean, it wouldn't work out, it wouldn't look just like this, but you can kind of count the little peaks in your little roller coaster as elementary steps. But this would be if these were together in a series of steps, this would actually be my rate determinant step because it has a higher activation energy, and this would be a faster step. So A is going to occur, it's going to be slower than B at the same temperature. So A, and you can also tell that A is endothermic because more energy went into breaking the bonds than it was released when forming the bonds. So there you go. And the other one, reaction B, is actually exothermic. Okay, here's your big chance. A reaction and its experimentally determined rate law are represented above. So there's the things. A chemist proposes two different possible mechanisms for the reaction, which are given below. So this is taken from a release exam and altered. So this is a good example of an AP exam question. Based on the information above, which are the mechanisms, it's consistent with the rate law, list the intermediates in each mechanism. So go ahead and take about 3 minutes or so to work on this one. Did you find one? You may have found more than one. Did you find one though? Yeah, there's two mechanisms. There's one on the left and there's one on the right. Do y'all think both of them? Yeah.
Yes.
So the rate law has X2 in it, and so that would mean that X2 would need to be the reactant in the rate determinant step or the slow step, and so that does work for mechanisms 1 and 2. Did you list the intermediates in each mechanism?
Yeah.
Okay. So let's check it out. Both are consistent. So intermediates, let's just look at this. First of all, neither one of these has a catalyst because a catalyst would be something like, I don't know, let's pick a letter. So if I had something, Z, I think a Z, well, whatever. And so if you look, if it starts and it comes out at the end too, then it's a catalyst. It has to be at the beginning and the end. Do you remember that? Yeah. It's like a Cadillac. It helps you get there faster, but you're in it when you start and you're in it when you leave, right? So it's present in both of them. So anyway, if we look, I'm going to circle the intermediates, and so those are the things that are kind of created along the process. So to me, it looks like several different intermediates, right? So they're produced and consumed within the reaction. It looks like X, this X here, that's produced and then consumed. You see it? This is produced, but it doesn't. This one's produced and then consumed. So in this first one, they had X and XY2, which I circled, and then in the second one, they had a few more. They had X, and then they had XY, which you can see here and here. They had Y, and then they had X2Y. And so you can see that those are created and consumed, created and consumed, created and consumed. So those are your intermediates. You got it? Okay. Alrighty. Yay! The rate law for a reaction is found to be rate is equal to K, A to the second power, and then B, concentration of B. What is the intermediate? Which of the following mechanisms gives the rate law? This has got a lot of practice for you. Oh, okay, got it. Did you find it? This one's got an intermediate, so you kind of have to think a little bit, okay? First of all, I see y'all figured it out. Which reaction is it? It's 2, right. So let's talk about that. We need the rate law to be A squared and then the concentration, so the concentration of A squared and then B. So if we look at this one, this is the slow or the rate determinant step. You see it now? Yeah. So I would want to write the rate law, like if you're not paying attention, you would write the rate law as E and then A. So you'd write like K is equal to, rate is equal to K times E and A, just to the first power. But you can't have an intermediate in the rate law. So you have to follow the intermediate back and write what it came from. So if I follow this E back, it came from an A and a B. So let me kind of help you out with that. So if you're not paying attention, you'll be like, rate is equal to K, and then A and E. Well, that's not okay because that is an intermediate. So what you're going to have to do is you're going to have to replace the E with where it came from, and it was created by an A and a B. And so if I substitute that in, then I find that my rate law is rate is equal to K and then A squared and then B. How you feeling? Now you got it? Good. I love this. I love this question. Draw and label the axes for the energy profiles below. Match the curves with the appropriate description. So let me kind of show you what this does. There you go. See, we don't need to. There, I drew the curve. I drew the axes in for you. But basically, just on your paper, go. You know, letter, 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 letter. Just do like that. So we're matching up the letters. When it says two-step mechanism, one-step mechanism, that is the number of elementary steps, okay? And like I said, you can kind of count your little roller coaster heels as a step in the mechanism. I hate to be that simple, but that is it. The reason why you have these little peaks is because each individual step will have its own unique activation energy that has to be overcome to break bonds in that step. Got it? Yay! Okay, so let's go ahead and start. So A, it's exothermic, and so when you're figuring out something is exothermic or endothermic, you need to look as far as potential energy is concerned. What much potential energy you start with and how much you end with. It does not matter what happens along the way if you're looking at endothermic or exothermic. If this, where you end, is lower than where you start, energy was released as exothermic. Yes.
So the slow step's always gonna be the one with the higher activation.
Yeah, the slow step or the rate determinant step, just say so, that's fine. That is going to be the one with the highest activation energy, absolutely. So, two-step mechanism where the first step is slow, and you can see that the activation energy here is greater than here. So the activation energy for the first step would be from here to here, and the activation energy for the second one would be from here to here. Okay. So, anyway, B, if we go ahead and label that one, is going to be the one beside it. And you can see here that it's endothermic because where you end is higher than where you start. So energy had to go into the system. And the second step is slow because you can see here the activation energy of the second step is higher than the first one. Starting to get the hang of it? This one is C, and so that you can tell that's exothermic, and the second step is the slow one. And on D, you can see that this is endothermic, and the first step is slower. Yeah. And then E, we only have one step here. So guess what that means? it would mean that when I write the elementary steps, there would only be one. So that's E, and then there's F. Any questions on those? Piece of cake? No? Yes? You good? Okay. Catalyst, yay! A catalyst can stabilize a transition state, lowering the activation energy. So what that means, if you recall, like if we have a surface catalyst, sometimes gas particles can kind of adhere to the surface, and it can kind of hold them in place, and then, yes, sir.
I have a question on FRQs.
Yeah.
Do we need to use a rate determining step or is it okay if we slow step?
It's the same. They're used interchangeably. And what they'll do is they'll probably say, determine the slow step, right? And so you'll just say that. But they're the same. It's like saying, I don't know, I'm trying to think of two things that my brain is broad. But yeah, it doesn't matter if you say slow or rate determining. Some people call it like RDS or something, rate determining step. A catalyst can participate in the formation of a new reaction intermediate, providing a new reaction pathway. So, like I said, sometimes like a solid, like this is an example of a heterogeneous catalyst where you're using something in a different state of matter to kind of the gases will kind of hold to the surface, and then they will be able to get the correct orientation. There you go, a heterogeneous catalyst. I already said that, I didn't mean to. So like I said, the nitrogen and hydrogen is they're kind of adhere to the surface, and that helps them to correctly interact, a correct orientation. So there's your rate determinant step. That if you look at the activation energy, it's kind of hard to tell those numbers. I would need some data there, but a catalyst and acid-base catalyst reaction is either gaining or losing a proton. Surface catalyst, either a new reaction intermediate is formed, or the probability of successful collisions is increased. Basically, here's the deal. You're either going to come up with a new reaction pathway, like a different set of elementary steps that gets you to the same products, or you can use a catalyst, which, like a surface catalyst, for example, would help them to collide correctly. Those are kind of your two options, okay? In enzymes, they bind to reactions in a way that lowers the activation energy, and that helps with the correct orientation too. That's kind of biology related, and they haven't asked a lot of questions about that yet. All right, so we made it to the end of Big Idea 4. I'm super excited. Yeah, so you want to take a little break?
Yes.
Yeah, y'all look so sad. A week-long break. Got it. I guess so. Okay, let's go back and get started on Big Idea 5. This sounds so excited. So thermochemistry is Big Idea 5. Let me get this moving. I broke my computer with all our chemistry today. No, here it is. Okay, I've already said this a couple times today, but you can't say it too much. So when bonds are formed, energy is released, and when bonds are broken, that's going to take energy. Bond strength is determined by the distance. So what is that number that you're either putting in or getting out, that enthalpy needed, is going to be determined by the distance between the atoms and the bond order. And if you recall the bond order, like a second order bond is just a double bond, right? That's not rocket science. So multiple bonds, we have double bonds or triple bonds, that's going to shorten the distance and increase the force of attraction. So bond energy is always endothermic. You always need energy to break a bond. And so when you're doing the enthalpy for this, your delta H for breaking a bond, it's always going to be a positive number. So keep that in mind. And so, for example, if you're told that, negative 42 kilojoules per mole of energy is released when you make a bond, then that same amount of energy, positive 42 kilojoules per mole, is going to be needed to break the bond. See what I'm saying? Okay, so anyway, here's your single bond energies. So hydrogen, carbon, carbon. So you can just kind of follow this down. It gives you some energies, bond enthalpies. And so double bonds here, triple bonds. So they're going to give you these numbers. You don't have to have those memorized. So again, there's three factors. HCl is going to be smaller than HBr. So HCl, when you look at the math here, the bond enthalpy for that is 432, but the bond enthalpy for HBr, or hydrogen bromide gas, would be less because of the distance there. So you have a smaller Coulombic attraction. So we can continue to go back to Coulombic attraction when we look at bond enthalpies. Polarity, HCl is more polar than HC. So when we're looking at that, you can determine that, remember, through electronegativity. Bond order or length. And so if you look at a double bond, for example, here with this carbon and carbon, there are 4 electrons in this bond. And so there's going to be an increased Coulombic attraction between the nucleus of this carbon and the electrons from the other carbon, and the nucleus of this carbon and the electrons of the other carbon. Because there are 4 electrons involved in that area of electron density for bonding versus 2, for example, with a single bond. Okay. So the lowest potential energy is going to be where bonds are formed. Bonds, so when you see an energy diagram like this, the bottom, or the area on the graph that has the lowest potential energy will be where the bond is formed. That's how the bond was formed, right? To kind of lower the energy system, the energy state of the system, right? So lowest potential energy means that it's going to have the most stable configuration. Remember, if these atoms, they're too far apart, then the attractive forces are going to be weakened because of the Coulombic attraction is weakened by the distance. And if they're too close together, like if they start to overlap, for example, the repulsion of the like charges from the nucleus and the electrons will, increase the potential energy. So we want to, there's a kind of a distance that you're going to kind of find that happy place between repulsion and attraction, and so that is going to be your bond length in this case. So good times. Okay, so the bond energy for carbon to sulfur in CS2 is 577 kilojoules per mole. Is the bond energy of the carbon to selenium bond in CsE2 expected to be greater than, less than, or equal to this value? Justify your answer. So take a peek at the periodic table. That will help you. This one shouldn't take too long, maybe a minute and a half. Just one part. When you're thinking of some magic words you have to say, getting that. Got it? Okay, so if we look at the periodic table, we can see that sulfur is 16 and selenium is 34. So selenium is in the fourth period, and so it's going to have 4 energy levels, and it's going to be a larger atomic radius when we look at the value. Because of that, when it's bonded to carbon, the Coulombic attraction will be less because of the greater distance. And so I would expect that the bond energy should be less. And so, yeah, it has a larger atomic radius because selenium is larger. The orbital overlap will be smaller. So 1 point was earned for the, and now if you notice the date here, 2005, that's really kind of, they have kind of changed as far as that whole Coulombic attraction thing, and they really do like that. But they're still referring to the same thing. The orbital, I think if you went with Coulombic attraction, I think you're in a better place. This is a 12-year-old question. So it's not wrong, but, all right, maximal Boltzmann distributions. These come up so many times. Temperature is a measure, again, of average kinetic energy. The particles with a larger mass will have a lower velocity, but the same average kinetic energy. So, if you recall, in class, I sort of took 2 books, not 2 books. I took 2 little cars, like I stole 2 of my child's cars. I'm not good at drawing, so I don't care. But here I have one little car, looks like a spaceship, it's totally fine. There's the window, I give up. And then I had a larger car that I stole from my son, and it was bigger. And
Oh yeah.
and I hit them or pushed them with a book. So I applied the same, I laid them on the table and I pushed them with a book. And I applied the same amount of force to them, same kinetic energy. And if you recall, the lighter one went a lot farther and went a lot faster than the big one. And so they still had the same average kinetic energy, but the lighter one went farther and faster. And so if we're talking about gases, for example, if we have a neon gas and argon gas at the same temperature with the same energy, the neon will be going faster. Because, I mean, I told you in class, it's like a speeding bullet versus a semi-truck. You know, you could get it to where they'd have the same average kinetic energy that both kill you, but the truck wouldn't have to be going as fast as the bullet, right? So, anyway, it's kind of a little dark, but whatever. The distribution also, remember, is going to show you that at a higher temperature, more of the particles, right? If this is the activation energy, at a lower temperature, you're not going to have as large a number of particles that will have adequate energy to overcome the activation energy. So, anyway, increasing the temperature increases the number of particles that have the activation energy required. But you got to remember, you're not going to change the actual value of the activation energy. Just more particles will have sufficient energy to overcome the activation energy. All right, more practice. Woo! Consider 3 gases in a tank. Let's see. We have methanol, carbon monoxide, and hydrogen. How do the average kinetic energies of the molecules of the gases compare? And which gas would have the highest average molecular speed? I just explained this by drawing you a picture, so I think you got it. You go.
I got it.
You already got it. I think you learned this really well already. This was something we were good at. Maybe I should have brought more toy cars in for electrochemistry. That might have been necessary. Y'all want me to just, you got it. Yeah, okay. So super easy for you guys. So the average kinetic energies, are they any different, you guys? No, because they're all the same temperature. Yay. 1 point is that. I want this question. Don't I want this question on the AP exam? Which gas has the highest average molecular speed? So which one is the lightest little toy car? How about hydrogen? Sure. You know, that formula is on the formula sheet, but you don't really need to reference it in this case. But the one with the lowest mass will have the highest average speed. So, anyway.
So we can just say like the one with the lowest mass or the highest mass or lowest mass has the highest speed.
Yes, so here's the thing. Jonathan asked a good question. He said, do we need to just say the one with the lowest mass? Yes, if they're all at the same temperature.
Okay.
Right. If you look at it, okay, I'm going to explain the math because I'm kind of sad that I didn't because, math is fun. Look, here's the deal. The kinetic energy, y'all just told me that kinetic energy for all three of these is the same because the temperatures. I love children. Are y'all seeing about laughing? Okay.
I can't do it.
Okay, I was explaining this. The kinetic energy for all three is the same, right?
Yeah.
So if this mass is smaller, what's going to happen to the velocity to get that same number? It's got to go. It's going to have to be larger. Remember, when things are multiplied together to give you a constant value, as one goes down, the other one has to go up. So they're going to be inversely related. That's why, if you wanted to reference it that way. All right. So thermodynamics and the vocabulary for it. The universe is the systems and the surrounding system is where what we're studying. The surroundings of the environment outside of it. Endothermic heat or enthalpy is going to have to come in. Exothermic heat is going to flow out. So if you feel something and it feels cold, it is endothermic. If you feel something and it feels hot, it's going to be exothermic. That's not good enough, but that is something. We already looked at the potential energy diagrams and really discussed that in detail of actually how that works. All right, here you go. Calorimetry. Woo! Everybody loves calorimetry. A student performs an experiment to determine the molar enthalpy of a solution of urea. The student places 91.95 grams of water into a coffee cup calorimeter and immerses the thermometer in the water. After 50 seconds, the student adds 5.13 grams of solid urea, also at 25 degrees Celsius, to the water and measures the temperature of the solution. As it dissolves, apply the temperature is shown below. According to the data, is the solution of urea and water an endothermic or exothermic process? Justify your answer. So if you see this and you're like, I hate calorimetry, I'm going to fail the AP exam, and you just feel really defeated, is this a hard question? No. So look, you see all these data and charts. It could be like really intimidating, but don't let it. Yeah, even on the hardest FRQs, there are questions in there that you can do. So go ahead and do this one for me. This one is a little bit tricky because you're recording the temperature of the water. So think about it. Think about it first. Think about it. Come on, Ralph. You guys okay? The graph is showing the temperature of the water. So, and actually of the solution. So they start at 25 degrees Celsius after 50 seconds. So here's 50 seconds, right? He's going to add the urea, or she's going to add the urea. And then the temperature decreases down to, 21.8. Okay? Do you have your answer? Okay. So you got to think you're putting a compound in the water. And if you're thinking now, be careful here. We have been looking at these potential energy diagrams, all day. So this is a little bit different. But the temperature of the water decreases. Where did that energy go?
Into the urea.
Yeah, so energy had to go into dissolving the urea. Okay, so is it endothermic or exothermic? Endothermic. If we were looking at a reaction coordinate and we were looking at potential energy, does this look endothermic or exothermic? It looks exothermic if we're thinking about potential energy and bonds and stuff. So you got to think about what you're actually looking at. So the process is endothermic. The decrease in temperature indicates a process for the dissolution of urea across water. Yay! All right, heat transfer. Kinetic energy is transferred between particles of varying temperatures. Heat is always going to flow from higher energy to those that are colder. When the temperature of both particles are equal, it's in thermal equilibrium. Not all the particles will absorb or release of the same amount of heat. Specific heat capacity, right? So if we're looking at the formula sheet, the specific heat capacity is this CP here. And so, yeah, I can't, there, oh, whoops, sorry. I was trying to just point to it and I accidentally touched it. My bad. So the CP is the specific heat. So Q is the heat, or the enthalpy, and that's mass, and that's specific heat, and delta T is the temperature change. So they'll give you the specific heat capacities of everything, so don't worry about that. So here's an example of that. Assume that the specific heat capacity of the calorimeter is negligible, which you can negate it, you can ignore it, and that the specific heat capacity of the solution is 4.2 joules per gram times degrees Celsius throughout the experiment. Calculate the heat of dissolution. So it's asking you to calculate the heat. I'm going to go back to the data because you need it. It's asking you to solve for heat. So you know which formula and you know what letter is heat, right? I'm going back. There you go. So there's your data that you need. Calorimetry is the only situation really that it's okay to leave data in Celsius. Right? Pretty much everything else you're going to want to go to Kelvin. And it's also another situation where it's okay to use grams. Like most of the time you're going to be going to moles. Tate, you got it?
Don't we add the masses on this one?
Yes, yes, yes. On solutions you're adding the masses. Absolutely. For the solution you're going to want to add the masses. Yes, yes, yes. And it gave you specific heat. If you can't remember if you're supposed to add them together, check it out. It gave the specific heat capacity of the urea and the water together. So that should be your big neon yellow sign in your head that says you need to add them together.
Oh, we did this one.
Yeah, we did.
It's 4.21. This isn't joules too, right?
Yes.
21.8, yeah.
Yeah, this is going to be joules. And the way you can tell it's joules, you guys, so you were just asking me what's the units. Look,
Yeah.
it's all right here for you, right there.
Wait, so does this mean game changing? It's endothermic.
You didn't know that. I thought it was 4. Yeah, 4. 91.95. Yeah.
Cross.
No, it was 4.2 up there.
Yeah. Is it, Ms.
Yeah.
Freeman?
Yes.
Is it 4.2 or 4.12
It's 4.2 for the specific heat because I have trouble saying that because it's for the solution, right? You're adding the masses together to get the mass of the solution. You're using the specific heat capacity instead of the solution as well. I'm seeing 3. Yeah, if you look, the temperature here was recorded with a 0 at the end. So 3, right? And then you'll have that decimal place when you subtract. Well, when you subtract, don't you get your delta T is only 4 point? Is it?
Supposed to be in joules.
Yeah, it's that in joules.
So I guess it would really be 2 sig figs. Wait a minute. No,
3 joules.
hang on.
I think you just looked up
The specific heat capacity is 2. Well, that's kind of one of those constants. But the temperature change is also 2, isn't it? When you subtract the temperature, don't you get a 2 sig figs?
Well, it was 1.8 minus 75.
So when you subtract, you're limited.
Oh.
Yeah, it's 2, right?
I think you just looked at like the problem and looked at
The data that you use in the problem.
the,
Yeah, they use 2. Let me talk to you about it. Please make sure you add when you're doing a solution. When you're making a solution, you need to add up the masses. Now listen, if you were doing something where it was like you put a piece of hot iron in water, you don't add those masses. That's actually a different animal, okay? But if you have a solution, you do find the mass of the total solution, and you do use the specific heat capacity of the whole solution. And they'll kind of give you that. So, anyway, you already told me it was endothermic. If you ended the problem and you had a negative enthalpy, a little red light in your head should have went off and said, ooh, I'm wrong.
Where
Did
did you
you-
get that other negative in front of that mass?
Where do they get the negative? You have to use your head and go that, yeah, the energy that is, the energy that is absorbed by the water was the energy that was released by the, yeah. So listen, you knew it was you knew it was endothermic, so if you stopped the problem and you were happy with the negative enthalpy, something should have went off in your head and said, no, that's not right. But yeah, when you're doing these solutions, the water is going to, in this situation, the water gave the energy that was needed by the urea to dissolve. The enthalpy had to be positive, even though when you subtract, well, I guess you got what? Did you get the temperature change went down, so it's negative, but the answer is not negative. So if you notice here, you get 1 point for the correct setup, but if you a correct numerical result. So if you didn't have if you got negative 1.3 times 10 to the third, no good. Okay? Be careful there. You knew the answer, right? You knew it was positive before you started. All right, conservation of energy. The first law, energy is conserved. It can be, transferred from one form to another. Work, negative power, and then your change in volume. And this is like a piston thing. Anyway. So if we talk about work and then it's negative P delta V, surroundings of that gas in this piston is going to expand, pushing the piston up. And I mean, this is kind of a physics thing. It does talk about it a little bit in our learning objectives, but it hasn't really been tested like that much. So anyway, conservation of energy when mixing. This is what you just did, right? The energy lost by the system is equal to the opposite sign of the energy gained by the surroundings. So the energy that was lost by the water was the same energy that was gained by the urea as it absorbed the energy to break apart. So be careful there. And so all that, when you look at it, energy is going to be conserved. So this is calorimetry. That's what you just did a second ago. You can use calorimetry to solve for heat capacity of the calorimeter, specific heat capacity. So anyway, this is, again, what you guys, some of you messed up on. The energy of the system is equal to the negative enthalpy energy of the surroundings. So be careful there. Again, the energy of the reaction is equal to the negative energy of the calorimeter. So think about it. You'll be able to reason your way through as long as you don't go through on autopilot. There's the formula that you just used. And when calculating the delta H or the enthalpy change, you have to take into account the mass of the reactant that caused the reaction. So in that situation that we just did, you need to make sure that you're adding the mass of the solute and the solvent together. Okay. Let's do this and we'll be done. Okay, a student investigates the enthalpy of a solution for 2 alkali metal halides, lithium chloride and sodium chloride. In addition to the salts, the student has access to a calorimeter, a balance. So this was last year, okay? This was a last year question. And a thermometer. So to measure the enthalpy of the solution for lithium chloride, the student adds 100 grams of water initially at 15 degrees Celsius to a calorimeter and adds 10 grams of lithium chloride starting to dissolve. After the lithium chloride dissolves completely, the maximum temperature reached by the solution is 35.6 degrees Celsius. Calculate the magnitude of the heat. Notice it says magnitude here. So in this situation, you're going to want to just have absolute value, right? So the magnitude of the heat absorbed by the solution during the dissolution process, assuming that the specific heat capacity of the solution is 4.18 joules divided by grams times degrees Celsius. So in kilo unit. And, you know, it says the heat absorbed by the solution, so if it was me, I would just go ahead and do the sign. Like I mean, you know how to do it. Just go ahead and do it.
So it's asking for the solution.
Yeah, so you need to make sure you're adding in the mass of the lithium chloride. Your mass should be 110 grams, right? And then notice they gave you, again, they gave the specific heat capacity of the solution. So that's your ticket in your head to go, oh, okay, I need to add these masses together. I need to use everything for the solution. Everything needs to be uniform throughout this process. It is asking for the magnitude of heat absorbed by the solution. So careful there. You guys got it? Did your formula?
Yes.
Yes? All right, let's check it out. So anyway, there's all your information. And it was asking the energy absorbed by the solution, okay? It wasn't asking for the energy needed to dissolve it. If it was asking, so when you got this positive enthalpy here, that's fine, because it was saying absorbed, right?
Yeah.
Got it? So, you got it?
Yeah.
Yay! I think we'll start there next time.
Great.
That was a lot of fun.
I can't believe I